So this is Professor Faiyu, not Wang. It's wrongly written Wang. He is Professor Faiyu. He's the Dean, Department of Electronic and Communication Engineering at Nanjing University. He's a wonderful researcher. He's leading a very good team. He's a collaborator. So I have been working with him last 2 months. I was with him, literally a very wonderful host, wonderful researcher, wonderful professor. So many students working in his lab day and night. I saw, he's a good researcher, always available. You call him. He doesn't use WhatsApp. He uses just WeChat, and just send him any message. He's readily available. And he's publishing so many papers in a year on antenna. He got, I think, 3 anaerobic chambers. Am I right, Professor Faiyu?
Yes. We have 2 anechoic chamber.
Yes, and wonderful facilities for gigahertz frequency measurement. One vector network analyzer is up to 110 gigahertz.
Yes. I will give a brief introduction on what we have here.
Yes, and he is also open to take our students for masters, for PhD, for postdoc, and we recently, working on different projects. So I'm supposed to work in his lab 2 months in a year, and we are coming out with some joint publications for high frequency application, for EMI, for antenna miniaturization, and so on. So it's a beginning, and let's hope for the best. So I'm going to hand over the dice to Professor Vikas Lahariya.
Okay.
And
Thank you.
yes, and we are here patiently going to listen you what you're going to say, and our students, they're going to inspire from your speech, and definitely at the end of session you will have some questions to answer.
Okay.
Shishani.
Thank you, sir. Honored dignitaries, HOIs, HOD, faculty member, and dear participants. A very good morning to all, and warm welcome to you all on the 3rd day of the 4th National Conference on Multifunctional Advanced Material MAM 2023. We feel immense pleasure and honored to welcome eminent personalities among us as a resource person for this session. To start with the technical session of the day, I would like to take an honor of inviting the first speaker of the day of the session, Professor Faiyu. Professor Wan is a Dean, Department of Electronic and Communication, Nanjing University of Information Science and Technology, China. He has vast academic and research experience. Faiyu, senior member of IEEE, received the PhD degree in Electronics Engineering from the University of Rouen, France in 2011. He was a postdoctoral fellow with the Electromagnetic Compatibility Laboratory, Missouri University of Science and Technology, Rolla. He is currently a full professor with the Nanjing University of Information Science and Technology, Nanjing, China. His current research interests include negative group delay circuits, electrostatic discharge, electromagnetic compatibility, and advanced radio frequency measurement. He will be delivering a talk on the integrated circuit electromagnetic compatibility testing method using TEM cell. He will be joining us on the online mode. So please, over to you, sir.
Thank you, Chairman. Thank you for the invitation from Professor Thakur. So I will share my screen, okay? Is it okay? You can
Yes,
can you see?
Yes, sir.
Okay, thank you. So I start my presentation. Hello, everyone. My name is Faiyu. I'm from Nanjing University of Information Science and Technology. The title of my talk is Integrated Circuit EMC Testing Method using TEM cell. The talk is divided into 3 parts. First, I'll give a brief introduction of the background of EMC, of the integrated circuit. Then I give a TEM cell's design. The third part is IC EMI testing based on the TMCL. First, I give a brief introduction of my university. Nanjing University of Information Science and Technology. It's a NUST. It's founded in 1916 and renamed from Nanjing Institute of Meteorology in 2004. So I think our best subject is meteorology. And in 2017, NUST is one on the list of the China's double first-class construction university and disciplines, as well as Jiangsu high-level university. So our university has over 30 undergraduate students and yeah, this is the location of our university. It's about 300 kilometers from Shanghai. This is Shanghai. To Nanjing, about 300 kilometers. From Nanjing to Beijing is about 1,200 kilometers. So this is our university. It's quite long. From this is the east to the west, about 3 kilometers. So our lab is here in the west of the universities.
Hello. Not 3, it's 300 kilometer.
3 kilometers.
3 kilometer.
Yeah, 3 kilometers.
Okay.
The university is 3 kilometers, not 300. Okay.
No. I thought you were talking about Shanghai.
Oh, no. From Shanghai, yes, it's 300 kilometers. From Nanjing to Shanghai, yes, 300 kilometers. So this is our lab. We have one large microwave anechoic chambers. So the chamber size is 70 meters long, 8 meters width, and 8 meters height. So it works up to 110 gigahertz. So all our equipment like the VNA or spectrum analyzer and the scope, all the equipment works up to 110 gigahertz. And we can measure the 2 meters by 2 meters. The size of the antennas can be 2 meters by 2 meters, and the weight can be 150 kilograms. So normally, if you have a radar, if it's not for Navy, for Marine, I think all the radars you can put on this here, and you can measure the antenna patterns here. So this is our microwave anechoic chamber here. And we have another one is the EMC laboratory. This one is our EMC lab. The size is 7 meters by 4 meters and by 3 meters. It works up to 80 gigahertz. It's standardized for EMI, electromagnetic emission, and EMS test. This is our EMI receiver here. So basically, we have two anechoic chamber. Here I give a background of the EMC of integrated circuit. So for the China, every year we have a department we call China Electronic Information Engineering Science and Technology Department. They give challenges in the technique. So last year they give 16 technical challenges. And one of them, the 9th, is the electromagnetic field and intelligence, Internet of Things. All these things have a great development in China, and all kinds of these equipments are facing serious electromagnetic security problems. So broken through the constraint of traditional thinking and method, we need to establish new theories on the electromagnetic environmental effects and productions. So all these information electronics and its applications are important challenges currently facing this field. So how the integrated circuit affect the electromagnetic environment Because this figure, they give a brief introduction of the role of integrated circuit in a complex electromagnetic environment. Here, this is the bottom. There is some material like what Professor Atul did in MIT University. The materials, the chip technologies, packaging, and even then, based on this material, we designed the integrated circuit or system in chip or SOCs or MEMS. This is we call device levels. Then all these device levels, then we with antenna with other passive circuit, we become the PCBs and subsystems or systems. Then with all these systems, we can compose the complex electromagnetic environment. So we think that all the emissions are from the ICs because IC or integrated circuit or system in package or system on chip, all these things are active circuit. And other things like PCBs or antennas or other things, they are passive circuit. So if there's no emission from the ICs, then we don't care. We don't need to care about PCBs. But of course, there's the IC is a strong emission source. So we need to measure the emission from the ICs. If you can control the emission from the ICs, then we can have a good electromagnetic environment here. So this is the ICs. We think integrated circuit is a critical part in a complex electromagnetic environment. So how they have some international standards to measure the EMI from the ICs. In fact, for subsystem or system, they also have many EMC test methods. But for the IC test, there are only two. One is IC 61967. This is test for EMI test for emissions. Let's see, it could. We have the TMCL method or wideband TMCL method. Or we have the surface scan method. We have many methods here. In fact, I think for EMI test, up to now, we may have 11 methods to, but different parts. Some is, for example, measure the radiated emission. This is also the radiated emission, but some are conductive emission, and some are different frequency bands. This is for EMI test. Also, we have some other immunity tests. Immunity test means that if we have a strong disturbance there, we put the IC in a strong disturbance. We check how the IC survive in the strong disturbance. So they have some IC 62132. This method, this is a standard method for international standards. They also have some TMCL method. This is for radiated immunities. They have BCI method, the background injection, and so DPI method. They have many other methods like this. This is the international method here. So we need to talk about the development trend of integrated circuit. As we know, the integrated circuit develop very fast. For example, the continuous increase in complexity. Let's take Huawei chilling 990 SoC, for example. They use the 7 nanometers fabric technologies. They have 10 billion devices inside the SoCs. So they combine the power supply, the radio frequency, digital signals, analog signals, and sensors inside the same package. So in this SoC, they have everything inside. So you may see the RF circuit and the digital circuit, and they may have some influence on analog circuit and also on the sensors. So they have an EMI problem inside the system. Now also the power supply voltage is decreasing. They can become 1 volt. When I was in universities, our system works something like 3.3 or even 5 volts, but now it's below 1 volt. So it can become the system can become weak. And the working frequency is getting higher and higher. It can be 10 gigahertz. For example, the 5G. For Americans, they use millimeter wave like 24 gigahertz. But in China, maybe now it's below sub 6 gigahertz. But in the next 5 years, we'll move to millimeter waves. So millimeter wave basically we mean we will work up to maybe 28 gigahertz. So the working frequency is high. And also the input-output data rate is faster. It can be 10 gigabits per second. And it will become maybe 20 in the next 5 years. So stronger. If a dynamic current is increasing, the basically meaning conduction, emission, or radiated emission are become stronger. Also, if we have everything in one package, so you have a poor EMC within the system. So in one system, your EMC problem inside the system is weak, and also the noise tolerance is decreasing, and a bit to resist EMC or EMI is become weaker. Of course, it's using 7 nanometer technology and compared to 180 nanometer technology, they have a different ESD abilities. So ESD problem is become a severe problem in the ICs. So this we said, okay, IC is become critical in the IC design. So here we give a brief introduction on TM cell design. We have a basic introduction, characteristic impedance design, or analysis of resonant frequency and cutoff frequency and performance of TM cells. So TM cell is they have a different series. In fact, but most of the, I think only one in the market is from an American company called FCC. They have 5 series with GM1, GM2, GM3. They're just based in a different frequency band. In GM5, maybe now it works up to 3 gigahertz. GM3 is about 2 gigahertz. In fact, this is a simple microwave equipment, but it costs about 50 kilo yuan. There's nothing, just a passive circuit. They cost you 50 kilo yuan. Is this very expensive equipment? But this one is very useful. For example, they can be used for immunity test and also emission test. For example, for immunity test, less than 3.7 millimeter wave of input power can generate electric field of 10 volts per meters, and 72 and 37 volts can generate an electric field of 1000 volts per meters. That basically means, as you know, for EMC lab, the most expensive equipment are power amplifier. To generate 50 volts per meters from, for example, 10 kilohertz to 80 gigahertz, it costs about 2 million yuan. But for if we use a TM cell, for example, just to test ICs, we can use some very small, some only 37 watt. It can be maybe 37 watt. It can be something like 10 kilo yuan. So also you have a very excellent field uniformity and lower standing wave ratios and low insertion loss. It's low cost, easy to operate, and easy to achieve automatic testing. So this is the TM cell method. So here we hope that this signal can work in 50 ohms. So we have some calculation of the character impedance. We see the impedance is basically determined by this equivalent capacitance. So it's coupled we give equations to how to calculate the capacitance here. So basically, this capacity is controlled by omega and also the H and the A and B here. The width and the height and the width of this inside corner of the this transmission line. So we do some simulations. We find that the width can be, for example, 98.3 millimeters. The main section, the character impedance can be 50 ohms. But they also have some, because this is a closed system, so we need to have transition sections. Transections means this we need to keep the impedance to be continuous to 50 ohms. So we have some introduction. So we need to do some optimization on this. For example, the G, the size of the G and the X here. So the G can be 9.3 millimeters. Then after that, we'll shield this gap with some connectors to have a closed system scale. So they have some cutoff frequency and the random frequency, because for a rectangular waveguide, we can calculate the random frequency here. But this system is not a rectangular waveguide. This can be the both sides of the TMCL is closed. In fact, so we treat it as random cavities. So with the random cavity, you can use this calculation to calculate the random frequencies. So here is some simulation of this S11 and S21 of the. We see that the random frequency is about 2 GHz. So below 2 GHz, we have a good performance. S11 is below -20 dB, and the insertion loss is most 0.5 dB. So this is a cross-section electric field diagram. It's electric field diagram. 2 GHz. So we see that the random frequency can change the performance of this. So this is a field uniformity analysis. So this is TMCL with different planes. We have, for example, 20 millimeters, 28 millimeters, 70, 38, 37 millimeters. We have the field uniformity. We found that the uniformity is less than the difference is less than 2 dB. So this is quite good compared to anechoic chamber. In anechoic chamber, the standard can be 6 dB. So 6 dB is size. For example, if we will measure the UT, we will measure the TMCL without the UTs. We find that it can be a good performance. But if we put the UT, that basically means you put the IC inside the TMCL. After that, you measure the TMCL performance, it can change. So we have this one-third criterions. If the size of the UT is less than 1/3, we still have a good performance. This is same when you work with antennas. For example, if you measure antenna in the anechoic chamber, you have a good performance. But if you put antenna in the real application, if you store it in a tank, in other systems, you will find the change, the patterns will change. So this is a test result. We see that below 3 GHz, our performance, the performance of this S11 standing wave is quite good, and the insertion loss is higher than 3 dB, so it's better than 3 dB. So this is can satisfy our test. And we also have solutions for the up to 5 GHz, even 7 GHz for TMCL. We just reduce the TMCL to a small size. This is also, FCC also gives this standard method, standard TMCL. They sell this for 50, maybe 60 kilo yuans. So within 0 to 5 GHz, S1 is less than -70 dB, S2 is greater than 1 dB. So this is a measurement result is quite good performance. So we have solutions for different TMCLs. One 3 GHz, another one is 5 GHz, which is similar to FCC's product. Okay. So with this our TM cells, we try to do some measurement, some test of our TM cells. This is for emission test. Of course, it can also for used for immunity test. Here, you see we can put our ICs in the bottom of the circuit inside the TM cell. Then the emissions will coupling to this transmission line. Then with this thing is connected to our connector, then transmit to the spectrum analyzer. So with this spectrum analyzer, we can measure what we have, what's the emit from the TM cells. This is called radiated emission test in TM cell. Okay, this is a standard method. Then we need to do the test. We need to have some standard PCB design, because ICs they cannot work with single ICs. So we need to install the ICs in side test board. The IC has given some standard test board here. We have 4 layers, 1 layer is ground, one layer another.
Hello, Professor Wan. Hello, Professor Wan. We are not able to hear you. So I think there is some network issue.
Okay, it's okay.
Hello?
Yes, sir.
Can you hear me now?
Yes, yes, sir.
Okay, thank you. I continue the talk. Okay. I'm sorry for the bad internet.
No, it's okay, Professor Fayu.
It's okay now?
Yes, perfect.
Okay, thank you. So they also have some, we treat there some software activities cause some large difference in my problems here. For example, if we use serial communications, or we use some ADCs or some temperature sensors or some SPI communications, we found that software can change the emissions quite different, quite big. If you check the maximum value here, and the different, they can have a different maximum value and different frequency. It can be, for example, 51. The maximum for ADC 51 dB millivolts, but for the SPI flash it can be 3.87 points. So their big difference can be 3 dB different, and temperature and the frequency difference can be quite big. So the software, as we say, the software activity can cause a large difference in ICs because the EMI emissions. So here, so with our TMC IC EMI testing both on the TMCL, with this TMCL, we can give some IC EMC testing here. So for the standard method, we only have some square standard board. We can only measure the 0 degrees, 90 degrees, 180 degrees, and 270 degrees. We have only 4 degrees here, but as we know, the ICs can be, the current direction can be any angles. So we try to analyze the angle effect of electromagnetic radiation in TMCL here. So the radiation of microstrip line in the TMCL here. So the output of the emission of what we measured, what we get in the spectral analysis is this V voltage here. But there are two mechanisms. One is E-field coupling, and this coupling is constant without the effect of the angles because it's directly perpendicular to this transmission line. Another one is a magnetic coupling, is a function of the angles. For example, ICs have different directions, the coupling to this transmission line can be different. So we found that this IC EMI can have a strong angle effect to the maximum radiation here. So this is the radiation of IC in TMCL here. We have found these different angles. So to analyze the effect of the angles, we design one square, another one is round test board. So with this round test board, we have a starting point. We have this copper fixture. We have starting point, then we can move these angles to different to compare to the starting point. We have any angles here. For example, we can change it by 10 degrees by each. Then we put these angles in the TMCL. We measure this, use amplifier, use spectrum analysis to analyze to measure the emissions here. Then we compare the square method and the round method. For example, the square method, we're using different serial mode here. For example, in square method, the 180 is this angle is a maximum because. But for the round method, we found that the maximum is 170.
Hello, Professor Fayu. We are not able to hear you.
This is something different with the standard method. So this one is a near field scan method. We can use this near field scan circuit gear. Then we measure we can measure the distribution of electric field. We found that the chip clock circuit is a maximum gear. So before that, we don't know which one in which part is the most maximum emission gear. So this is what we did here. We have some scan system. We have the integrated circuit. We have some app system. We have a spectrum analyzer to do the near field. We did some near field scan test, near field probe to do the test. So, but what we measured is emission from the ICs, but we cannot separate which one is E field and which one is H field. So here we can have some hybrid methods to identify which one is the E field and which one is the magnetic field. Because if we put the DUT located in the center of the TM cell, then the E field coupling generates two responses that are in phase. They both are the in phase. If it's in phase, we connect here, we use the sum, we can get the E field. Then the magnetic field, they generate two out of phase response. So out of response funds, we measure it here, then we can get the magnetic field probe. So the sum part of two voltage rate is proportional to the electrical field coupling. And this the difference of the voltage is proportional to the magnetic field coupling. So with this method, we can separate E field and the magnetic field. Here, so this is the E field and H field measurement. We can have in a different angles. Here is 0 degree and 90 degrees. In most cases, we find the emission are similar. They are most similar. There's no big difference. But in some parts, there are quite a big difference. We think that is caused by software problems, software activities. Here, for magnetic field probe, the 0 degrees and 90 degrees are quite big difference. The emission of H field in 0 degree orientation is worse than 90 degrees. So it's quite difference can be 19 dB, 9 dB, so it's very big difference. So this indicator current flow in 0 degree directions. But in fact, if it's really in the 0 degree directions, we don't know direction because I will say to the wrong standard test method to find maybe it's not 0, it can other degrees, but we have maximum values. Yeah.
Hello. I think you have to reset your VPN network, Professor Fayu.
Hello.
Just
Professor
hold on.
Fayu.
He is setting. Hello, hello, hello. Now we want to see you, Professor Fayu. Professor Fayu. So our next speaker is also ready, Professor Vivas from Taiwan. So we are going to welcome him. He is quite instrumental in signing one MOU between MIT University and his university. Two of our students, Mayuri and Shivangi, they are doing internship with his lab. And I think very soon we are going to get the copy of MOU. He's a very good researcher, PhD from Taiwan, and he's doing marvelous research work in refrigeration, mechanical engineering, and he's publishing so many papers. So we are going to welcome you also, but meantime, we wanted to ask some question from Professor Fayu. Can we start with Professor Vivas?
Yes, sir.
Okay.
Okay.
It is my honor to invite next speaker of the session, Dr. Vivas Panigrahi from National Chin Yi University of Technology, Taiwan. He is currently working as an assistant professor in National Chin Yi University of Technology, Taiwan. His research area is on multidisciplinary background span in the field of mechanical and biomedical engineering with a specialization in numerical as well as experimental fluid dynamics. He has been working as a research area of mechanical refrigeration and biomedical engineering with a specialization in fluid dynamics, multi-scale thermal management system, energy efficient fluidic window, microfluidic flow engineering. He would be discussing with us on the topic of thermal management of flexible electronics through microfluidic modular heat sink with integrate channel design and improve material characteristic. Sir, please, over to you, sir.
Okay. Thank you for the introduction. So can I share my screen?
Yes, sir.
Okay. So is it okay?
Yes, sir.
Okay. So thank you, Professor Atul and MIT University for inviting me to present my research sneak peek in the recent years. So like I would like to give you some glimpse about my lab and my university before proceeding to my topic. So first of all, we are a national university. Our name is National Chin Yi University. So we are located at the mid of Taiwan or the center of Taiwan, and we are surrounded by several industries, and we are basically a like we are basically a technical university. So we usually collaborate with local industries and try to solve their problems. So we currently have 12,130 students and 334 professors, and we have around 450 international students from 18 different countries. And we have a proper precision manufacturing hub within our university. So over there you can see some very cutting edge tools like 3D printing, metallic 3D printing, or like CNC, everything. So most of the industries, they come to our university, and if they have some research related to that, they would like us to address their issues. And our regional rankings is around 451 to like 500, and in the Times Higher Education ranking, we are like progressing in each and every year. And for the basically like there are some students from your side who might be interested for our master's and PhD degree. So we are currently offering at least 10 master degree and 3 PhD program in English. So if any students would like to join us for their master's and PhD program, we would like to support you through your journey during your study and stay here in Taiwan. So we are a very new lab. So we are consisted of around 5 to 6 students. So both local and as well as some Indian students. And in the last 2 years, we have basically built this lab, and we have some very modern 3D printer like FDM type printer and some SLA type printer, which can fabricate some precision, some precise microfluidic device, even some multi-scale devices. And then we have also some other imaging resources. And by using these resources, we are currently our research focuses are multi-scale thermal management, energy efficient fluidic window, flow engineering, 3D printing, HVAC components, and microfluidics. So I would also like to highlight, if some of your faculties would like to collaborate with us, we would be happy to do so. So we can discuss over phone, or we can discuss through email towards the scope of our research. And then in today's topic, it will be thermal management of flexible electronics through microfluidic modular heatsink with intricate channel designs and improved material characteristics. So in this aspect, I would like to first highlight the background, research problems, objectives. Then obviously the experimental section, I will discuss how we have conducted the experiments in our laboratory. Then we will discuss 2 different research, new research results we have obtained during the first 2 years. And then we will discuss all the future perspective. So as we see the electronics are becoming flexible day by day. So maybe you can see on daily to daily basis. So most of you must have must have seen that Samsung flexible phone. So most of the device nowadays you are going to see is becoming flexible by nature. So it's you can see the flexible electronics in LED screen, healthcare devices like some sensors, some intelligent sensors, some flexible microbot. There are some special microbots or micro robots. They are trying to use the flexible electronics, and you can see the along each section of the region, whether it is the Asia or the states, or whether the Middle East, or whether the EU region, the flexible electronics market is increasing with a significant rate. And that we can see between 2020 and 2027, you can see that there will be a cumulative annual growth of 6.8%. So this market is huge, and so do the opportunities and the other opportunities and the problems are also significant. So maybe I would like to show you one video so that you can take a look about the various electronic equipments or flexible electronic equipments are coming to the market. So you can see this is a tab. So where you would like to put on your lap and try to play. And this is another example regarding the flexible like screen. And you can see that the thickness is somewhere around 0.01 mm. So which is really thin.
Hello.
Yes.
Yes, sir. Please continue, sir.
Okay. So so can you see the video?
No, sir.
Okay. So actually, I am playing a video. So but it might be some issues. Okay. Okay. Anyway, let me like continue with my talk. Okay. So next. So next, let us let us go to the next slide. So as we as these electronic products are getting developed, so they are becoming also powerful, and to make them powerful, their brain or their heart, which we called as the IC chips, they are becoming denser, and we have to stack multiple layers to make them powerful and to work efficiently. So that you can see, for example, usually the laptop we were using before 6 years, which is around Core 2 Duo 66 CPU at 2.4 gigahertz. Their IC is providing a temperature around 63 degrees centigrade. But a latest laptop like AMD Radeon R9 290X GPU, their temperature is somewhere around 94 degrees centigrade. So if some of students, they would like to use the laptops for games, and they must have realized the amount of power or amount of heat they are generating. And it has been already realized that if the power if the temperature range increases around 10 to 15 Kelvin, then it doubles the failure of the IC chips. So at any cost, as the devices are becoming thinner and more powerful, so the IC chips are getting getting strong. So it is generating also substantial amount of heat. So and they are becoming flexible. So it is a big challenge how to towards their thermal management. So we can see, so ideally, if you open up your computer or if you open up your CPU, you can see some of these devices. So these are like traditional heatsink devices, which are basically metal, either made up of aluminum or made up of copper. So usually we provide a force forced convection in terms of airflow or forced airflow, so that the temperature from the bottom can transfer to the fin, and then the air can carry out that extra heat. So it has been realized for these powerful IC chips, these traditional heat sinks are failing. So nowadays they are trying to use the 3D printing and also topology optimization to make such devices. So which can be you can see these beautiful structures, and these are not beautiful, they are also very powerful and very efficient towards the thermal management of these IC chips. However, as the electronics are becoming flexible, so it is next to impossible to fit such kind of devices within the electronic items or within the electronic devices, because as they are metallic, we cannot make them bend, and we cannot fit, and due to their thickness and due to their size and dimension, we cannot fit them into the thin electronics, thin contemporary electronics. So what is the option? The option is microfluidic heat sink. So basically, we all know that microfluidics are made up of PDMS, like PDMS material, and PDMS material, apart from its transparency, they are very flexible. So it is a very useful and famous material. And along with the microfluidic devices, we can introduce some fluids. So once we introduce the fluid has a higher CP, or higher specific heat capacity, so that it can carry out a significant amount of heat from the IC chips. So there are several researches which have highlighted about the microfluidic heat sink. So particularly, like this paper is published, the left-hand side paper is published in Nature, where they were trying to co-design the microfluidic heat sink and the electronic chips. And similarly, in the mid chapter, they also have developed a 3D printed PDMS, like PDMS heat sink, which can be used for the towards the transfer of heat. And similarly, there are also various researches, but the major with these researches are the material we are using for the fabrication of the channel, which is PDMS. So PDMS has a very poor thermal characteristics. So usually that thermal characteristics means like thermal conductivity and also specific heat capacity. As it is very low and very less, it cannot effectively carry out the heat from the IC chips. So there are some microfluidic devices also which has utilized nanofillers. So we usually with the PDMS, we dope the PDMS with some fillers or some metallic fillers, or sometimes some carbon-based fillers like CNN, graphene oxide, etc., and try to mix it and then make the microfluidic devices. But the major challenge is that, so even if it is very difficult to mix the nanoparticles with the viscous, due to the viscous PDMS, and then it is also very difficult to cast it in for a microfluidic devices. So there are many fillers which can be utilized along PDMS to make the microfluidic devices. For instance, like the carbon fiber, like this is RGO or reduced graphene oxide, so etc. But the problem is that the viscosity of PDMS, it is making it difficult to fabricate the channels. And on top of that, we have realized, the latest researchers have realized the graphene oxide as an excellent material. It has an super or thermal characteristics, in terms of thermal conductivity and specific heat capacity, and it can be also utilized non-invasive towards the fluid, and also non-invasive towards any other samples. So some recent researchers also have highlighted, by adding just merely 1 volume % of graphene oxide into PDMS, the thermal conductivity can be 2 times higher than the PDMS. So overall, I would like to conclude the research limitation of the current microfluidic device from the material perspective and from the microchannel perspective. So from the material perspective, although elastic, PDMS possesses a poor thermal characteristics. And from the microchannel perspective, most of the microchannel now are being fabricated, they use soft lithography. So they can fabricate 2-dimensional channel. So it is also very difficult to fabricate 3-dimensional channel or intrinsic channel. So now we have by luck we have 3D printing, which can help us to fabricate the channel. But in case even if we are using 3D printing, how we can cast the PDMS geo nanocomposite. So our objective, the objective of this research topic is towards improving the thermal characteristics of the heatsink device, improve the material characteristics so that it can become more flexible, and then improve the microchannel hydrodynamics. In this aspect, we have first prepared the PDMS geo, and we have realized by using a shear mixer about a time frame of 10 minutes, we can uniformly mix the geo with the PDMS. Then we put the PDMS within the small bottles, and then we vacuum, remove all the extra airs. Then we cure it at 80 degrees centigrade. Then we get the after certain amount of curing, then we get the PDMS geo samples. Then we put the geo samples. We wrap them with strip foam so that we can make the heat transfer to check the thermal characteristics of the material. We wrap them around the strip foam and put them on a heater, and by using one infrared camera, we try to find out the various temperature properties of that sample. And then by using the normal heat convection and heat conduction equation, we try to find out the thermal conductivity and specific heat capacity at different temperature setting and different experimental condition. So, and it is also very challenging to fabricate the 3D printing channel. So what we have done, we first 3D printed the intrinsic channel, or the channel we want to make the microfluidic devices. Then we put it for casting, we make the mold, we fix the channel, we have printed, then we put it for casting, then we make the vacuuming, and then we put it in acetone to make the make the channels. And although this is a very easy, but yet it is a very effective technique. So I would like to highlight, if some of you would like to do the microfluidic research, they can follow this technique. To prepare their microchannel in a low expenses setup, and can to perform the experiment. So you can see we have make several types of channels. So the first top one is the triangular or intrinsic channel, which is next to impossible to fabricate with the traditional fabrication process. And the bottom one is the straight channel. And next, we also did some the elasticity test, or to we test the material characteristics of the samples, and by following the ASTM standard. And then subsequently we try to evaluate the surface roughness of the prepared samples, and we used white light interferometry in this aspect. And then for the experiment setup, this is the experiment setup we have utilized to calculate the effectiveness of our microfluidic devices. And we have tested various temperature and various flow rate in this aspect. So this is the real picture of our experimental setup. So you can see that there are some power resources which give continuous supply to the heater. We have put inside the 3D printed module, and then we put the PDMS geo samples or microfluidic device on the top of the heater. Then we provide some heat, and also provide through the syringe pump, we provide some DI water, so that we can we can get to know regarding the effectiveness of our microfluidic devices. And subsequently to to validate our experiment, we have also in the experiment we have the limitation that we cannot see through the plane. So it is usually we see from the top, so it is very difficult to see through the plane. To see through the plane, what is how the addition of the material is affecting the through plane heat transfer. We also have conducted the simulation, and also to know what is happening within the microchannel. We have conducted the simulation in the computer environment. And these are the experiment the numerical parameters. So we have solved the continuity, momentum, and energy equation. We have particularly used the ANSYS Fluent, the finite volume BM solver to solve this equation. And we have tested various There is flow rate like 10, 40, and 120. And we have also we have validated our result through grid independency test. And then once we once we have highlighted the grid, then we we analyze the data through the post-processing softwares. So so in the resultant discussion, I would like to highlight the two of my latest publication in this aspect. So for the first one, it is like microfluidic modular heatsink with improved material characteristics. And in the second, I would like to discuss what is the hydrodynamic influence on the thermal management of the flexible heatsink. So particularly, we have prepared the cylindrical sample, what we have discussed. So we put them on the hot plate, like 3 samples, like PDMS 2% geo and PDMS 5% geo, and then we track their surface surface temperature. So you can see this is the please look at this yellow color, and this yellow color means the heating, right? And you can see that 85C is the highest temperature, and you can see by adding the 5% geo, we can readily heat the surface, and also then we subsequently cool it for another 120 seconds. And you can see that among all the 3 samples, this PDMS plus 5% geo sample is easy to heat. You can you can see this maximum temperature is often for the 5% geo rather than the PDMS, and also easy to cool. So we have quantified the the samples, and we have realized by adding 2 and 5% geo, we can increase the temperature 1D temperature transfer around 18%, at least around 18%. So from that, here we validate our hypothesis that by adding the geo, we can increase the heat transfer and heat shedding process of the PDMS. And then we have also quantified the thermal conductivity at different temperature setting, and we have realized, for instance, we take the 85 degrees C, which is somewhere around 360 Kelvin, and we have we have shown you in the bar graph the average surface temperature on the top surface of the flexible top surface of the cylindrical object. And then we have realized by adding the 2% of geo, the thermal conductivity has been increased around 1.7-fold, and by adding 5% of geo, we have increased the thermal conductivity of PDMS by around 2.5-fold. And also subsequently, because as we are trying to fabricate the flexible heatsink, so flexibility or the material elasticity matters the most for us. So we also have tested when we add the graphene oxide into the PDMS, how the flexibility is changing. So we have quantified the elasticity, and we have realized that by adding the 5% of geo, or adding the 2% and 5% of geo, we have seen the increment of threefold of the elasticity of the PDMS material, which validates our hypothesis. By adding the geo, we can make some flexible heatsink which can be used for flexible electronic devices. Subsequently, we have quantified the surface roughness, and we have conducted the white light interferometry. So what it does, it usually take the surface take the picture of the surface roughness, and then try to interpolate the dots or interpolate the roughness through some post-processing software. And we have realized that by adding the 5%, if we add to whether we add 2 or 5% geo, our surface roughness is somewhere around 400 nanometer. So which has a significant improvement in the surface roughness of the material. And we all know that by increasing the surface roughness, we can increase the convective heat transfer coefficient, and that might accelerate the overall heat transfer. And then, like I have said, like we have we have fabricated the microfluidic devices. So the left one is the pure PDMS channel, and the middle one is the PDMS 2% geo, and then the right one is the PDMS 5% geo. And this is the this is the top surface of the microchannel, and you can see the middle one is depicts the dimension and the position of the microchannel, and we can see if we see the left hand side, we can see the the lowest temperature is morely related most of the places around the microfluidic devices. But if it is PDMS 5% geo, we can see the the temperature distribution of the temperature that is that is distributed properly throughout the surface of the heatsink devices. And we also have realized for so around 30 to 40 minutes, we observed the steady state. So within by tuning the flow, around after 30 minutes, around roughly after 30 minutes, we can get a steady state, and it can constantly it can significantly remove the heat from the IC chips. So for instance, I would like to also highlight, maybe I forget to highlight, this is the heater. So this mimics the surface the temperature of the IC chips. So further we have we have proceeded for the numerical simulation, and we have the left hand side, this is the experimental data we have observed, and this one is the simulation from what we have obtained numerically. And then we have realized around we have extrapolated the data around 2 individual lines along the width of the channel, and then we try to correlate it. And then we have realized around there is a very significant there is a good agreement between the two data set, and the R square, the cross correlation value is somewhere around greater than 0.8. So we have we have proceeded for further numerical simulation to see the through plane heat transfer within the microchannel. And you can see for the PDMS and PDMS 2% geo and PDMS 5% geo, if we see closely to the left hand side, so the heat transfer towards the top is the temperature or the temperature contours or the isotherm contours at the top of the channel. So this is the I dash channel. So we have tried to extrapolate this the top surface which is highlighted as plane A. We have tried to highlight the plane A, and then we have extrapolated the data from I dash location, so which we have plotted in the bottom figures FGH. So we can see that. So if there is if we also introduce the fluid flow, we change the fluid flow, or the the fluid, we tune the fluid flow within the microchannel, then even if we change the fluid flow to 10 to 100 microliter per minute, the increase in or the change in heat transfer is somewhere around 1.4 fold. And for 2% geo, it is somewhere around 1.5 fold. But you can see at the similar location for PDMS 5% geo, it is around 1.6 fold. So which highlights the variation in temperature along line 11 dash is more distinct, with an increase in the weight percentage of geo. And this paper is summarized as a in the Journal of Applied Thermal Engineering, which is quite quite distinct in our field, like this. And this is the recent paper we have published in International Communication in Heat and Mass Transfer. So the last month we have published this research. So here, we have I showed you initially, with the use of 3D printing, we can print some flexible or the intricate micro channel. So we have tried to make the 3-dimensional channel and also straight channel, and try to make the micro devices and put it for thermal characterization. A similar similar trend like the earlier, we can see from from this study. So where we can see for the PDMS, whether it is a triangle or whether it is a straight channel at a temperature of 85 degrees centigrade, we can see that the thermal propagation or the temperature isotherm distribution is very negligible within the corner of the microfluidic devices. But instead of that, once we have doped them with geo, then we can see at least some kind of temperature within the corner of the device. That implicates the temperature propagation throughout the device is quite uniform, and it is better in terms of PDMS geo devices. However, when we go to change the flow rate, and we have tuned different flow rate, we have observed a distinctive phenomena, which is not according to our hypothesis. So in our hypothesis, we say that if we make the intricate channel, it will improve the through plane heat transfer, and it will improve the overall heat transfer characteristics of the device. However, we have realized that this device one is the I believe device one maybe like PDMS triangle, and device two is PDMS straight. So we can see that for the at a low flow rate, this trend is very very stable, and it is according to our hypothesis. But as we improve the flow rate, or as we increase the flow rate, then we have realized the device one, the temperature of device two is higher than device one, and similarly, so it is also in accord to our device. But when we go to the device 3 and 4, it is in accord to our hypothesis. But for device 1 and 2, the trend becomes different. And similarly, for device 2, for the when the flow rate is more higher, the trend in the result that is just altering. So we were curious why this trend is altering. So initially we thought this might be the temperature, might be the issue of temperature. So we have conducted the experiment for several temperature for the device 1 and device 2, because for device 1 and device 2, the change of the device design is becoming altered, or is being altered to our hypothesis. But we have realized the same trend. So we can see that at a low flow rate, at a low flow rate, the PDMS has a higher temperature than the PDMS geo. That means PDMS geo has the lower temperature, so that the temperature is being distributed uniformly. But when we go to the higher temperature, then the PDMS geo based device is performing ineffectively compared to the PDMS device. So to know why it is happening, we have gone through the hydrodynamic analysis. So in the hydrodynamic analysis, we try to we make the intricate channel, and we try to take a particular plane and try to analyze the vorticity within the channel. So we have the velocity data, and then we have take the divergence to find out the vorticity. And it is it is very interesting to realize that at low flow rate, we cannot see any vortices nearby the channel or near the bend of the channel. But as the flow rate is increasing for the intricate channel or for the triangular type of channel, we can see the vortices. Particularly if the flow rate is becoming bigger, then you can see the vortices around the corner is becoming more. So this is also contradicting with our with the earlier research findings, where the most of the researchers they have observed, except few, most of the researchers they have said that the vorticity is is towards the betterment of the heat transfer. But it is not like the case, and we have realized also some recent research articles from from one of Indian University and one from Imperial University. They have tried to highlight sometimes the vorticity within the channel makes the makes a local hotspot temperature within the device, which which makes the device becomes more hotter with the time, rather than making it cool. It it makes the things more it averts the heat transfer process within the channel. And we have also quantified the to confirm our finding, we have quantified the the circulation, and we have quantified the circulation somewhere around circulation for the when the flow rate is higher, it is much significant, the maximum strength of vortex is much significant compared to the low flow rate. So this is a quite new and interesting finding, and that's why this paper has gone with the for the publication in International Communication of Heat and Mass Transfer. So we have realized, as the conclusion, I would like to highlight that we have realized by adding the geo, we can improve the thermal characteristics of PDMS, and by adding 5% geo, with 5% geo, we can make the we can make the flexible heat sinks. And then we have realized also by adding the 5% geo, we can improve the thermal conductivity by around 2.5 volt, 2.5 fold, and also by increasing the doping geo, we can increase the specific heat capacity as well as elasticity somewhere around 3-fold. And then we have realized, if we are trying to make the intricate channel, we should try to make the straight channels rather than the intricate channels. And if we are currently we are doing some research more about the intricate channels. Hopefully we'll get some results very soon, and we'll try to send the results to for our subsequent pods. And we have realized that particularly if you are planning to make some intricate channels, at any cost you should avoid some sharp bends or some sharp sharp angles, so that you can minimize the strength of vorticity and strength of circulation. So if you would like to know more about these two research, I would suggest you to look for my paper, which has been published in last year, the first one regarding the PDMS geo devices, which is in Applied Thermal Engineering. So it is quite a prestigious journal, or maybe in this journal. So this is our recent paper in the International Communication in Heat and Mass Transfer, which highlights the hydrodynamic influence on the thermal management of the flexible heat sink devices embedded with out-of-plan intricate microchannel. So I would like to conclude my talk, and thank you, Professor Atul, for inviting me, and also I would like to show my gratitude to Amity University towards giving me this opportunity to showcase my recent researches. And if any of the faculty would like to collaborate or do some researches or some student exchange program, please feel free to contact me in my email or via any communication medium. Okay, thank you.
Thank you, sir, for such an insightful and a fruitful talk on the multi-scale thermofluidics. The session is open for questions. Any question or the discussion? So I believe our audience must have got benefited from such an informative talk. To proceed this session, I'm delighted to invite our next speaker, Professor R. Arun Kumar, Vice Principal and Professor of Pharmacology, Chettinand Academy of Education and Research Institute, Chennai, Tamil Nadu. He is also a Director of IQAC of Chettinand Hospital and Research Institute. I request Professor R. Arun Kumar to enlighten us with your thoughts on the local drug delivery in medical practices. He will be joining us in our online mode. Professor R. Arun Kumar. Sir.
One second. Am I audible to you?
Yes, sir.
I can proceed now with the presentation.
Yeah, yes, sir. So please start.
Are visible? Are you able to see the slides?
Yes, sir.
Okay. Sorry, I think I have not opened my camera. Good morning. Before I start, I think I need to thank the organizing team and also my good friend Dr. Ankush, who is with us for the past maybe 1 year or so. In this topic, which is local drug delivery system. I don't know, I'm a medical person and I'm dealing with drugs and devices at my clinical practice and also, at research level. And I guess most of the audience are from maybe engineering or maybe paramedical. I'll try to give some basic idea or overview of what we deal in medical practice or in health institutes when we talk about drug delivery. See, there is something called conventional drug delivery. See, when we have a disease, when we have a problem, health issue, we take medicines. Now, those medicines or drugs are given in various routes. Orally we administer, like we have tablets. Tablets are solid, formulations. We have white color tablets. We have coated tablets. It looks like red color or yellow color or different colors. We have capsules. We have soft gelatin capsules. We have liquid formulations. Like we have very many formulations that we use, orally. Similarly, sometimes in emergencies where we don't have much time. I believe that you are able to see the slides, right? Are you able to see the slides?
No, sir.
You don't see the slides?
Sir, please.
Do you see the slides?
No, sir. Only first slide it's seen.
The second slide?
No, sir.
1 second, I'll just do some corrections. Do you see this now?
Yes, sir.
Is the slides changing?
The slide is conventional drug delivery. Yes, sir. Yes, sir.
It is
You can continue.
Is it comfortable, all of you, to see it?
Yes, sir. You can continue.
Yeah. Now what I was saying is that when we have a health problem, we choose to give them medicines in various routes. When the condition is not an emergency condition, we give the medicines orally in various forms, maybe tablet, maybe capsule, maybe liquid. Various formulations are available. Sometimes when the condition is critical, we admit the patients in ICU where the patient is unconscious or semi-conscious. We cannot give them oral medications. We give them injections like intravenous injections or intramuscular injections. The challenge here is that when the drug is given, let's say orally or intramuscularly, usually it is absorbed from stomach and then it is distributed throughout the body. And the drug action is possible in whole of the body. If we intend that the drug should act in the brain, every part of the body also will receive the drug. Maybe heart, maybe kidney, maybe liver, maybe skin, maybe everywhere the drug is distributed. So the challenge here is that you want the drug to act only in a very specific area, which is not possible now because the whole body is exposed to the drug and the whole body will receive the drug and the drug will bind to the receptors in various organs and you will have whole body effect of the drug only, not a very specific local effect. And hence the chances of adverse events are possible. When we take drugs, there are unwanted effects we experience. For example, we take a drug for cold, we feel sleepy. This is an adverse event of a drug because it is acting in an area where you do not want the drug to act. And again, the dose that you need to give an effect is large because you are giving, let's say, 500 milligram of a drug. What you really need is only 50 milligrams, but you end up giving 500 milligrams because only then 50 milligram will reach your target zone. So these are the two disadvantages that we see with the conventional drug delivery like oral administration or intramuscular administration. And the challenge here is that the delivery of the drug at the local area is challenging, and hence you need a large dose, and then the adverse events are possible with conventional drug delivery. Now, when we talk about local drug delivery, what is the purpose? We want a very specific local action of the drug. And it is not just, when we talk about local drug delivery, we can also give a drug locally for systemic action. So there are two reasons why we give local drug delivery. Number one, we want the drug action only in the very specific area. We are applying a cream in the skin. We want the action only on the skin. We give a drug in the oral cavity. We have an ulcer in the oral cavity. We give a drug. We want the drug to act only in the local area. But sometimes we give drug locally. We want the drug to act systemically. For example, I can tell you, just to make you understand, we have a condition called rhinitis. What is rhinitis? It's common cold. And there is something called allergic rhinitis. These people, these patients will have, severe sneezing, nasal secretions, eye secretions. Why? Because they have allergy in the nose. So we give a corticosteroid as a spray in the nose for local action. The patient is relieved of the symptoms of sneezing, itching in the eyes, itching in the nose, and all other conditions. But same nasal route is a local drug delivery. There is a hormone called calcitonin. Calcitonin is a hormone that we give it for bone weakness. We call it osteoporosis. So we are delivering calcitonin in the nose for the hormone to be absorbed from the nasal mucosa to act systemically. So when we talk about local drug delivery, we don't really mean only local drug delivery, though many times what we mean is we are giving a drug locally and the drug should act only in the local area. It is not absolute in terms, because sometimes you will also see the drug from local area is absorbed. Why is it absorbed? Because every organ has got a blood circulation. Nose has blood circulation. Though I am delivering the drug in the nose for local action, some amount will be absorbed through the perfusion of the blood in that area, and it will act in the all other areas. So there is nothing like really a local drug delivery in that sense. Our intention is to deliver the drug locally, but a part of the drug will also be absorbed and will give a systemic action. The advantage here is that we give a very minute dose, and only a very, very minute dose is going to be absorbed, and hence the adverse events will be very, very minimal. Though local drug delivery is meant for local action, sometimes you use this mechanism for administering a drug for systemic action. With these two examples, you can clearly understand that allergic rhinitis, we give corticosteroid using a nasal spray for local action. Very minimal corticosteroid is absorbed, providing very minimal adverse event. The other example is that osteoporosis is a bone weakness. After 60 years or 70 years, we may have that problem. There is a hormone to treat it. It is called calcitonin, and it is given as a nasal spray, but not for local effect, for bone effect. Okay. So when we talk about local drug delivery, there are various areas where we administer the drug using, you have a pocket there, you have a source there, you have an anatomical site which is located there. We have an eye condition. We give drugs in the eye only. For conjunctivitis, we have redness in the eyes, we use eye drops. It is one of the oldest and classical way of explaining local drug delivery. We have the problem in the eye, we give eye drops in the eye for local action. Intravitreous is inner side of the eyeball. We have some problem. We can inject the drugs also into the eyes. It is intravitreal local drug delivery. Intranasal, I have already briefed you in allergic rhinitis, we are giving it. Now intranasal, we can also use it for systemic drug delivery. Then oral route, you have a lot of, oral, liquids for after ulcer. We have oral ulcer, we give analgesics topically in the oral cavity. And we have, corticosteroids given orally as a topical paste. We are applying it. And in bronchial asthma, we are giving drugs inhalationally for local drug delivery. And rectal route, where we defecate, we give drugs in the rectal route. For example, enema. One of again oldest routes of drug administration for local drug delivery is the rectal route, where we have constipation. You're not able to have a pleasant defecation, and we have our bowel movement once in 3 days or 4 days. We give enema here to evacuate, which is a local drug delivery. And intrauterine contraception, where the reproductive age group female doesn't want to become pregnant, but at the same time wants to have the family life, intercourse without the risk of getting pregnancy. We have a copper T. Again, more than 50 years we are using copper T, intrauterine devices. Then we have vaginal delivery of drugs. Okay, so these are various areas or anatomical zones where we deliver the drug locally. And then in skin, again, oldest local drug delivery. When we talk about it, we always talk about skin, dermal delivery. We have topical application, cream, ointment, and then we have injections given intradermally. We have injections given subcutaneously for local action. For example, if you see BCG vaccine, every one of us would have received BCG vaccine. How do we give it? Intradermally, to initiate immunological reaction, then to give immunity against tuberculosis. And then stent, people are having myocardial infarction, cardiac problems, we use stent, coronary artery. And then in the spine, we are giving injections, epidural and subarachnoid injection. And then where we have problem, we give the drug in the lesion itself. For example, we have an abscess, we take antibiotic, we inject in the lesion itself. And we have wart. Wart, I'm sure all of you will know it. What is a wart? Okay, it is a protrusion in the skin which gives a verrucous appearance, and we don't comfortable if it is in the face, if it is in other parts. So we tend to give injections in the lesion only. So this slide will give you an overall idea of what are the various drug delivery modes that we will use in our clinical practice or medical practice. Now these are the systems. This slide was talking about various routes in the human body which can be used to deliver a drug. Now these are the systems or devices which are available with us. We use this device to deliver the drug in the local areas. Ocular implants. We have the implant which can be placed in the eye, and the implant will have a drug which will be delivered for, let's say, 10 days or 50 days or 1 month, and we need to replace that implant once the drug delivery is complete. Cardiac stent. I will have further slides to highlight more on these aspects. Cardiac stents for heart problems. We have the stent and we deliver the drug there. And in the uterus, we can keep an implant. And then suppository is another term that we use to deliver a drug in vagina or in the rectum. And then we have implants in the brain to keep an implant to deliver the drug. To indicate how do we use stent in myocardial infarction, you see here that this is the blood vessel, and the blood vessel has got a block, and that's why we get myocardial infarction or heart attack. Now, what do we do here? We can do a bypass surgery. We can open the chest, and then we can, do a bypass surgery, connecting another blood vessel to this blood vessel, so that the blood circulation is proper there. That is an invasive procedure, a massive surgery, and people take a lot of time to recover from that. Instead, what we do now is that we have a catheter from our axilla or from our neck or from our hands or sometimes from our thighs. We insert a catheter through the blood vessel, and then we insert the catheter to heart. And if this is the blood vessel which is supplying blood to heart, and if you see here in the block here, I put a stent, a mechanical stent here, so that the block, if you see here, the block is not blocking, obstructing the blood flow here. This is the stent that you see, with a lot of fenestrations. A stent will be like this. So in the blood vessels, this is inserted and this will expand, and it will reduce the block so that the perfusion or blood flow is maintained. Now the problem with this stent, this again may go for block. So how do we reduce this block? We give drugs like tacrolimus, sirolimus, or everolimus. We coat this stent with the drug so that the stent is there, which will reduce the mechanical obstruction, and the stent will also release the drug, and it will act locally. These drugs are very toxic. They will produce anemia, they will produce bone marrow suppression, they will produce severe adverse events if you give them orally or as an injection. But in this method, if you impregnate this stent with this drug, very, very minute dose of the drug will be delivered locally. This will act in this tissue and will reduce the reblock or block that will happen after 1 year or 2 years. And this is a system that we have right now. Cardiac stent, compared to traditional stent, this drug impregnated stents are little costly, but the government of India has given a ceiling limit or upper limit of the this one, wherein people are now able to access it with 25,000 to 30,000 rupee for one stent. Previously, it used to cost 1 lakh rupee for one stent. Now, even drug impregnated stents are costing less compared to conventional or traditional stents. Now, for diabetes mellitus, we know that the problem is insulin deficiency. We use medications to increase insulin secretion. Drugs, some of you may be diabetics, maybe senior people. Some of them, these tablets will not be working. So we end up giving them insulin injections, and insulin injection is acting systemically. It's not really local drug delivery, though we give insulin injection subcutaneously or as intravenously. The reason is that insulin should act every part of the body. But the problem is that it doesn't reflect the physiology. What is the normal physiology? We take food, it goes to stomach, and it stimulates pancreas to secrete insulin. This phenomenon is lost when we give insulin in our thighs or in our abdomen or in upper limb. So we have insulin pumps. This will deliver insulin like how naturally insulin is secreting from pancreas. This pump is given or connected to our abdomen, our blood vessels, this is where normally we have insulin secretion. What this pump does is that we take food and the sugar increases, this pump will push insulin in the abdomen. From the abdomen, it will be distributed, mimicking the normal physiological secretion of insulin. This is insulin pump, which is picking up, though it is very costly. People are using it. I am a diabetologist, and for a few patients, select patients, I am using this because people have to be literate. They need to be really educated to understand the concept and use this insulin pump. This is automatic pump. We need not measure blood sugar, but it will release insulin like how normally pancreas is secreting insulin. And this is the device that we have it to deliver the drugs in asthma. I hope you all understand what is asthma. Asthma is a condition where we experience breathlessness, especially in cold climates or whenever we have infection. The respiratory tract goes for contraction and we find it difficult to breathe. Even in COVID-19, many of you would have experienced the breathlessness. Okay, so what do we do here now? There are tablets available like salbutamol or levosalbutamol. When we take that medication tablet orally, it does act, it does relieve the bronchoconstriction or the breathlessness. But the whole body is exposed to the drug and you will experience tremor, you will experience palpitation, you will experience sweating. These are all side effects of drugs used for bronchial asthma. So what do we do here now? We have this inhaler, or we have this rota caps, or we have a nebulizer. What is inhaler is that if you see this pump has got a medication loaded with high pressure here, and when I compress this, the drug will be delivered through this mouth end. So I need to keep this inhaler in my mouth. I need to press it. The drug will be delivered in my oral cavity, and at the same time I need to inhale it actively so that the drug is taken into lungs and the drug will act locally. Now this way we can reduce the dose enormously, and also we can reduce the side effects like palpitation and tremor. This will cost anything from 400 to 500 rupees for about 100 doses. There is something called in rota caps. Here, because it is highly, it is costing more, poor patients may not find, they may not be affordable to it. So we have capsules loaded with the medication. We put it in this, device, and then we open the capsule inside it. The powder will be spilled in this device. So I need to fix it in my mouth and I need to inhale it. This 15 capsules will cost about 100 or 150 rupees. So instead of 450, 500, you can, finish your treatment in 10 days or 5 days, which is 100 rupees. Now, when you are so breathless, you are not able to inhale this. This, if you see here, it is a compressor, and we load the medication in this, and then we fix it, nebulizer. Many of you may have used it. Fix it in the, mouth, covering mouth and nose. Now this pump will pump the drug very actively into my lungs. Where we are using this, I am so breathless. I am unconscious. I am breathless. I am not able to inhale the drug. I don't have the muscle power even to inhale this medication. I use nebulization. So asthma and other lung diseases, when we want to deliver the drug locally in the lung and respiratory tract, we use either inhaler or dry powder inhaler or nebulizer. Nebulizer where the patient is not finding enough power to inhale the drug or he is unconscious, we use this. Where the patients are active, we can use these devices to administer the drugs. Ophthalmology or eyes, I've already highlighted it. We can use implant for glaucoma. Glaucoma is the pressure condition of the eye where the intraocular pressure is increased. We can use a medication. The problem with eye drops is that you have to take it 3 times a day or 4 times a day, every day for 1 year, 2 years. We may find it difficult to use the drugs so frequently. So we give an implant, like we insert an implant here. It is there for 15 days, 1 month. It keeps delivering the drug. Or sometimes where this is the eyeball, you have lens, and this is the front end, you have the eyelid here, and from here only you see it. You have the lens, and the light falls on the retina, you see the vision. You get the vision. If you have infection here, we can straight away inject the drug here. We can implant intravitreal ganciclovir implant. People with HIV, AIDS, they get this problem of visual impairment due to this infection in retina. Here you have infection. So we implant this drug ganciclovir inside the eye, and you get relief from the viral infection. And then we have nasal drops, nasal spray. I was talking about it. Many times we would have used it. We have nasal congestion, we have nasal block, when we have common cold. We are not able to breathe properly. So we have this nasal drops. We give this spray, and people get relief from the symptoms. And this is for allergic rhinitis, where people are having severe sneezing for months together. We give medications in the form of a spray. The advantage is that systemic adverse events are reduced. Oral cavity. If you see here, the most challenging part of delivering a drug in the oral cavity is that we cannot make it to stay there in the oral cavity because we swallow. Correct? Unlike, in the skin, we apply the ointment, it stays there for 4 hours, 5 hours. But here, it may not stay for much time. That's the challenge here. Any one of you in engineering field or drug delivery field, if you could, develop some system with which we can deliver the drugs in the oral cavity, then you are hitting a jackpot. We have some paste. The problem is that we apply it in the oral cavity. When we swallow it, it doesn't stay there for a longer time. So some of you can take up some research in this, and if you want some idea or some input with regard to the diseases with which you can work on it, or the drugs that you want to work on it, we can always help, because we are a healthcare institute, and if you are working on some materials or some technologies, we can help you. We are also a dental college and hospital, so we will be interested to work on some of the devices where you can tag it with some antibiotics and push it in the dental caries. Drug is delivered for 2, 3, or 5 days. Instead of taking the medications as injection for 5 days, with one implant, you can finish it. You need to work on degradable nature of the device that you are working on, and how to deliver it. We are interested to even collaborate with engineers or material science people. Oral cavity is something which is very difficult, and in case all doctors look for some device or some system with which we can deliver the drug. We will deliver the drug for systemic action and also for local action. Many times we are using corticosteroid, paste or cream or ointment to give local effect, but we also look for systemic delivery of drugs. For example, if you see, again, oldest, I have myocardial infarction, meaning that I have heart attack now, I have chest pain. What we use now is that there is something called, nitrates, isosorbate dinitrate, isosorbate mononitrate. These tablets are available. I just, they are called sublingual tablets. I take a tablet and I keep it beneath my tongue. The drug will be released in no time. It is absorbed and then it relieves my heart attack or chest pain that I get in my heart attack. So these are systems which are already available. You can try to improvise on these systems, and any medical input is there. Some of the young graduates or research scholars, if they want to discuss with us, we are open. In fact, Ankush is there. You can coordinate through Ankush, and we can help you to form some hypothesis of developing drug, our requirement, our diseases, and the potential drugs that we want to use in problems in oral cavity. Now, this is in brain. If you see that, brain is very delicate. There are malignant conditions in the form of, like, let's say, glioma or sarcoma or meningioma. There are many conditions. Now we do surgeries, we do chemotherapy, we give radiation also. Everything is toxic in malignancy. So what people have designed is that there is a drug, carmustine, which is useful in brain cancer. Instead of giving it as injection or tablet, we get a drug delivery device or a pellet or an implant. So you can see here that doing a very minimal neurosurgical intervention, we open the skull and then we implant it into the tumor. So the drug is delivered inside the tumor. You can reduce the side effect that is going to happen with carmustine and all other areas, and you can ensure very precise delivery of the drug with very minimal side effects, and you will have a good outcome of a tumor. And there are drugs which are given systemically for local effect. See, we are delivering a drug in the local area for local effect and systemic effect. And we are delivering a drug systemically for local effect and systemic effect. If you see here, we are tagging the medications or drugs with liposomes or with antibodies or with isotopes, so that we can very efficiently deliver drugs in the local areas. For example, even in COVID, we had fungal infection. We are using steroids and we are using amphotericin B tagged with liposome, reaching. If we have fungal infection in brain, the drug will be delivered in brain. If we have fungal infection in the lungs, the drug will be delivered in the lungs. Like that, we can focus, tagging it with liposomes, we can deliver the drug in the local area. Cancer therapy, we are tagging it with liposome. Liposomal doxorubicin is there. Liposomal paclitaxel is there. And antibody tagged drugs, very many are available. I mean, in breast cancer, we are using it. We are giving as injection only, but the drug is delivered in the local area. These are various technologies and systems that we have. Routinely, we are using it in our medical practice. And I have tried to give you an overview of what we are routinely using it and what can be interesting for you when you want to take up some research initiatives. If you see here, we are also giving drugs in the joint, in the bones. Somebody is having, septic arthritis. I mean, knee joint. We have infection. We have drugs which are useful. When we give it as an injection, the whole body is exposed to it, and we will have side effects. Instead, what we do is that we take one simple injection, and then we load it with some antibiotics and corticosteroids. We simply inject it into the joint, and it relieves the pain and it reduces the sepsis. Sometimes even inside the bone, for example, you see a big lengthy bone, tibia, femur. So we did take the drug and then inject it into the bone also. So these are all something which we are already doing. All the various drug delivery routes that I have spoken here, and the drugs that I have mentioned here, and the devices that I have mentioned here, we are already using it. But we'll be happy in case if some of you want to collaborate with us. We'll be very happy to collaborate with Amity University with the organizing team, Professor Dr. Atul Thakur and the Director of Amity Center for Nanotechnology. He is the one who has invited me actually to share some of the medical aspects of local drug delivery systems that we commonly use. With this, I think I have come to the end of my short presentation. I have tried to restrict my speech only to 25 to 30 minutes for the time that I was given here. And before I conclude, I need to thank once again Professor Dr. Atul Thakur.
Thank you, Professor Arun. We are really fortunate to have you here online, and we have Dr. Prasanna, former secretary in MCI. So he wants to speak.
Vanakkam, Radhakrishna. Your talk was highly educative. I was the person who gave the permission for your medical college also.
Very happy, sir.
Letter of permission.
Yes.
Okay. See, you have extensively covered the topic and it was highly educative and very simple language. I thought you are a good teacher for pharmacology. It appears you are a universal teacher.
Thank you, sir. Thank you.
Especially when we have to interact with non-medical person. I just want one suggestion from you.
Yes, sir.
This is a scientific body and you are a medical man. What do you want this scientist to look at the new things? What is your challenge in medicine? We have got so many things, like we have COVID nasal vaccine.
Yes.
We have, I think more than 100 routes you would have told.
Yes.
But what is the route you are thinking should be the challenging route?
Yes, sir.
Thank you.
Excellent question, sir. Most challenging in terms of finding a solution for this. The problem that we always face is that right now we have exhausted antibiotics. We have exhausted almost all the domains. What is challenging to us is malignancy is challenging. Orphan disease. Orphan disease is that there is only a small set of rare diseases. For example, muscle dystrophy or autoimmune diseases or rheumatoid arthritis. In these diseases, there is no safest drug delivery route that is available. Whatever we are using right now, they are all conventional drug delivery routes, which is giving a lot of toxicities. In fact, we used to say that the patients experience more pain out of our treatment than the disease itself. That is the challenge that we are having it. We are not able to find out a precise device or material or mechanism by which we can deliver the drug only to the area where we want to deliver the drug. That is not possible even now. Even when we find out some solutions, the challenge is that biodegradability is not there. We can give a mechanical device, but that will be there in the area for a long time. Even after the drug is delivered, we need to do another surgery to remove that device or implant that we have kept it. So we are looking for the scientists to give a solution to find out a material which is inert, which is biodegradable, which will be staying in a local area for 1 month or 2 months or 3 months. We are finding it very difficult to get such material which is biodegradable, which is biocompatible, which is not giving any adverse event on its own. This is one challenge that we are looking at. The second one is that oral drug delivery is extremely challenging for the reason that I highlighted. When we deliver a drug in the oral cavity and we want the drug to stay there for 4 hours, it doesn't stay because with the saliva, it gets dissolved and then it goes into my stomach. So instead of staying in the oral cavity, the drug is reaching my stomach, which I do not want. I end up only getting adverse events. So the challenge that we always look for is that we are not getting biodegradable, biocompatible material with which we can coat or we can impregnate the drug and then we can administer it. Number one. And number two, we don't have a material which will stay in the oral cavity for 4 hours or 6 hours so that we can coin or we can tag that material with the drug and we can make a oral drug delivery possible. These are the two challenges that we always have. And everlasting challenge is insulin. I mean, there are even people who are talking negative about it, that the pharmaceutical companies do not want to market a drug which can be taken orally for insulin. Inhalational insulin was marketed before 4 years or 5 years. The brand name was Afreeza in US, Afreeza, but it is not successful. So if somebody is going to coin a mechanism with which we can, maybe a tablet, maybe a capsule, or maybe some other form, we can push insulin into it and we can deliver it into GA tract. That is again challenge, and nobody has been successful in it. Maybe some of, I believe that material science people or nanotechnology people can do some work on it. The challenge is that insulin is a protein. We take it orally. The proteolytic enzymes destroy insulin. That's why we are giving it as injection, subcutaneous or intravenous or inhalational route, which is a failure route. So if somebody is able to find out a mechanism of coating insulin, resisting proteolysis in our GA tract, they will create a big boom for India. I mean, government of India is promoting Make in India and doing basic research and taking some of the compounds globally. Even we can look for government funds if some of you come up with some idea about masking insulin from the proteolysis in GA. So these are the challenges in my view, sir.
I totally agree with you. See, for a good baby to come or good baby to be born, a good husband and wife is required. So if there is a good husband in pharmacology, there should be a good wife in the material people.
Yes.
So I think there is a marriage required.
Yes.
So if you can look at the priority areas,
Yes.
like diabetes, India is going to be the capital.
Yes.
We are already a capital in the population now.
Yes.
So now we are going to be the capital in the diabetes also.
Yes.
When we speak about capital, we are having a probably world's something like one seventh of the world's diabetes is in India. So if you can prioritize, and I think your medical college with engineering and so many multi-specialities, you can become a center for where the engineer and the doctors should come together, or the basic science person should come together. See, whatever challenges you have told, let us take this as the heading and have a, take 1 or 2 projects. If you want some fundings, I can help you to get it from the central government and all that. It is very interesting that you are doing wonderful work. You have DM pharmacology also?
And not DM, sir. We have only MD pharmacology, sir.
No. You start it. I will help you out. Okay.
Sure, sir. Definitely,
Right,
sir.
sir. Radha Krishna reminds me of the Teachers' Day. Radha Krishna again. Thank you.
Thank you. Thank you very much,
Thank
sir.
you, sir. Thank you. Thank you for the wonderful interaction. Now, I have one question, Professor Arun. We are quite expert in making ferrite nanoparticles and cobalt ferrite nanoparticles. They are having super paramagnetic properties, and they are good emitter of energy even. So can they be used for hypothermia treatment?
Sir, actually, I want to just highlight where we find it difficult to collaborate with the nano is. See, as doctors, as clinicians, we see that heavy metals are toxic to liver and kidney. Even when we collaborated with Ankush, now Ankush does, he used to use, let's say, mercury, or let's say iron, or many other, metals. The moment he comes up with some idea of generating a nano, component using these heavy metals, my first objection will be to nano team is that now I cannot use it systemically. I can try to use it as a topical application only. Even then, I need to ensure that it doesn't hit my liver and kidney. Okay. So when you are talking about cobalt, the challenge will be to ensure safety of the liver and kidney. In my view, it is going to be very challenging unless and until you are using a very, very minute, let's say micro or even less than micro, maybe nano or femtograms of cobalt or
yes,
mercury.
Of course, it will be in micron. It will not be like, more than microns. Yeah.
Micro is toxic because even in some of the traditional systems, maybe Tamil Paspam also we used to Paspam. Paspams are made up of with some heavy metals and then this one that gives toxicity to kidney and liver. So if you could focus on getting the nanoparticles with water soluble compounds. I don't know which is water soluble, which is not a water soluble, this one. So that the kidney will not take the burden, will eliminate it easily. Number one.
Right.
Number two, there are some metals which are safe to the body. For example, iron even at a high dose, it is safe to the body because we need a certain quantity of iron for every day. And minute amount of sodium, potassium, calcium, little bit of manganese or magnesium, they are all safe to health because we need them as a neurotransmitter or co-transmitters in our day-to-day physiology and biochemical reactions in the body. What is toxic? Like let's say cobalt, though we need a very minute amount of cobalt in our body, we are not happy to hear that a cobalt nanoparticle to be used systemically in some cancer or this one, because we know for sure that it is going to hit our liver and kidney. So this part maybe you need to, or we need to discuss mutually to get the safer compounds with which we'll be interested, so that you can work on that and we can establish the safety and toxicity in animals, and then we can take it to human beings.
Okay, great. Any other question from audience?
It's really nice talk, Professor Arun. And you have, in the last slide, you have explained a little bit about liposome mediated formulation.
Yes.
So whether you're using those liposome mediated formulation for the drug delivery?
Absolutely, sir. I mean, if you ask me that, personally, I did my PhD in liposomal doxorubicin. My PhD was related to, tagging liposome and doxorubicin and using it in ovarian cancer. And we have got a good pharmacokinetic results. And this 20 years or 10 years, traditional anti-cancer medications, due to the high dose and high toxicity, people are moving towards liposomal doxorubicin and other anti-cancer medications. There are few compounds which are already available. Like I was saying, paclitaxel is available, doxorubicin is available, and some of the antifungal medications like amphotericin B is available. But there is much more to explore in this area, because if we have about 100 anti-cancer drugs, only about 4 or 5 are liposomal right now. The challenge here is that at research level, it is okay. We can do liposome and then we can tag it with the drug, but commercial production standardization is very difficult, because the delivery of the drug in the target area is going to be highly variable depending upon how you are standardizing your method. Even liposomal doxorubicin, the innovator company has closed its factory for not able to standardize it, and only our Sun Pharma was able to meet the global demand of liposomal doxorubicin. The challenge was that we are not able to reproduce. See, one batch we are producing now, there is no consistency in producing the next batch after 1 month. This is the challenge. But at the research level, you can try to focus on, maybe we can discuss and we can give you some 5 or 10 medications that you can tag it with liposome and you can take it to the next level. But right now we have few medications with liposome available. The cost is though very high. One vial will cost 40,000 to 50,000 rupees.
Okay.
That's
so another question is that you have told that nanoparticles, heavy metal nanoparticles is really dangerous for the body. So whether we can, so
dangerous. I am only trying to give you a caution that heavy metals, we are worried because it may give us kidney and renal problems.
But whether we can use the carbon-based nanoparticles?
Absolutely. You need to give us some success in terms of drug delivery, in terms of favorable pharmacokinetics and pharmacodynamics. There are experiments which are available. If you come up with some proposal, I mean, we have a good animal house. We can do some preliminary animal studies in our animal house also. We can take it up as a research product. I mean, to the entire audience, in case if you have some interesting ideas and products with you, you want to evaluate in animals and humans. As a first step, we are open for such collaborations of doing animal studies and further to take it to the human studies also.
Okay, sir.
Prasanna was there and he was highlighting mutual collaboration should be there, and we are open for that also.
Okay. I'll mail you regarding the same.
Absolutely.
Thank you very much.
Thank you very much. Thank you, Professor Arun, for your informative and sparing the time. Dr. Ankush is there with you. I want to say hello.
Hello,
Ankush is
sir.
there, and I am thankful both to Professor Atul and Dr. Ankush for this opportunity.
Yes,
Good
thank you
afternoon,
very
sir.
much. Thank you.
Good afternoon, sir.
Okay, thank you. Professor Nagarajan is here with us. Ankush?
Yes, sir. Good afternoon. Good morning, sir.
Yes, very good morning. How are you?
I'm fine, sir. Thank you, sir.
Okay. Nice to see you.
Thank you, sir.
Okay,
Me too
thank you.
also.
Thank you. So Professor Nagarajan is here. Pravindra sir is here, a former director, SPIC, DRDO. Then Professor Anupama Thakur is here from Punjab University. So we'll have time to listen to them. So it's a short tea break. Tea is waiting outside. So let's meet after tea. Thank you.
The next session will start at sharp 11:40. Thank you.
Hello, everyone. Welcome back. I'm Dr. Neeru, faculty in MIT School of Applied Sciences, MIT University, Haryana. It is my privilege and pleasure to welcome you all in the technical session 2 of day 3 of National Conference on Multifunctional Advanced Material MAM2023. So after the online morning session, it is the time to shift from the virtual mode to the real conferencing mode and to hear the eminent personality sitting in the hall. For this, I'm honored to welcome Professor R. Nagarajan, Professor, Department of Chemistry, University of Delhi, New Delhi. Professor R. Nagarajan completed his PhD from Solid State and Structural Chemistry Unit, Indian Institute of Science, Bangalore, in 1993 under the supervision of Professor C.N.R. Rao. He has vast research experience working in prestigious institutions in India. He joined as an associate professor at the University of Delhi in 2005 and has continued to work as a professor since 2011. He has more than 200 international research publications. He has guided more than 25 students toward their doctoral degrees. His research interests include materials, chemistry of oxides, fluorides, and sulfides, structure property correlation in solids, layered hydroxide compounds, energy upconversion, and optical and magnetic properties of solids. So I humbly request Professor R. Nagarajan to deliver a talk on fascinating properties of materials, examples from our research. Sir, please. Yes, sir.
Yes.
Like it up. It's on the screen.
I sincerely thank the organizing committee members for the kind invitation, and I thank our former student, Dr. Neeru, for this kind invitation to attend this conference. I have been, this title of the 3-day conference, it says that it is advanced multifunctional materials. So I work on not, removing the advanced, I work on multifunctional materials. So the advanced comes in whenever you go into the real time applications, like you interface it with biology, or you interface it with other disciplines, then you introduce the word advanced. So whatever we are doing is some multifunctional materials. That means we work on a variety of properties. But for the time that is given to me, 30 minutes, so I'm going to concentrate on a few examples from our research. So today's outline of the talk is a brief introduction about what we are and what we are doing at University of Delhi. Yeah, thank you. And I will take the case studies of two systems. That is, one is titanium dioxide. Why titanium dioxide? You must be knowing about the titanium dioxide. Titanium dioxide is a solar, optically active compound that can absorb the UV visible radiation. And titanium dioxide, all of you also know, which if you are an engineer also, you would have come through the +2. And in the +2, they educate that titanium exists in the titanium 4+, which is a D0 configuration. Therefore, titanium dioxide is exactly white in color. Okay, all our watch dials, which are all white in color, they are all titanium dioxide coatings, actually. So another case study, which I'm going to take it up, is, this is a very active research area wherein people are working on battery systems. In the batteries, you have a cathode, you have an anode, you have an electrolyte, and sometimes the electrolyte can also be a solid electrolyte. That means it should be a conductor of ions from one end to the other end. So the second example is going to be based on that. And I will be concluding my talk with a few, things. This is my route. And therefore, I will always start with this route. Solid state reactions. That means, if you are taking two solids and if you are making them to react, first of all, what that has been taught to us is rate of the reaction increases with increase in temperature. That means if you are going to grind two solids and the reaction cannot happen at room temperature, it has to happen only at high temperature. And therefore, the solid state reactions, that is the reaction between two solids, now can be extended to the other things also, that a gas can react with a solid. Even that comes under solid state reactions. You can do intercalation and deintercalation. That is how our lithium cobalt oxide battery in all our mobiles that are happening, charging and discharging that is happening, is only because of the lithium that is getting deintercalated from lithium cobalt oxide and getting intercalated into the graphite layers. So that kind of intercalation is also considered to be the solid state reactions. And then you can also react a solid with a liquid, So this is a brief thing. See, there is always a question that comes to our mind, how to increase the rate of the reaction between the solids. See, if it is a homogeneous medium, suppose you are mixing a liquid with a liquid, it's very easy to react. But if you are going to deal with two heterogeneous substances, then how to increase the rate of the reaction. That is the dx by dt. So one of the ways of increasing the rate of the reaction is you can increase the area of contact between the reactants. What you can do, you can try to minimize the particle size by grinding or ball milling or freeze drying. These are all some standard techniques in which you can reduce the crystallite size, or you can reduce the particle size. If you reduce the particle size, you are increasing the surface area. If you increase the surface area, reactivity is more, right? And second is, you can increase the rate of nucleation. That means, structural similarity. If there is two different solids which are having similar structure, then they will undergo reaction very rapidly, And then third is increase the rate of diffusion of ions through various phases. See, suppose in the solid, if you are going to grind two powders, then the diffusion path length for the metal ions is going to be enormous. And therefore, that is why the reaction is becoming extremely slow. And therefore, if you want to enhance the rate of the reaction, then you better have to adopt a solution phase synthesis. I mean, that means everything should be starting from the bottom. That means everything should be in the solution form. And from the solution, you should be able to make the solid that is of your choice. So solution phase synthesis to make sure atomic level mixing, and which will certainly decrease the diffusion distances of these metal ions. So these three are the thumb rules with which we are going to adopt the synthetic aspects. So reaction between two solids and heating at higher temperatures, what are the disadvantages? There are a lot of disadvantages. You will always end up in thermodynamically stable product. That means delta G is equal to delta H minus T delta S. So the delta G is equal to negative product only. You are always going to get anything which is that is present as the intermediate. You will never be able to achieve if you are going to heat straight away at a very high temperature. And it is going to cost you huge amount of energy. And it is also cost you a lot of time. Okay. And atomic level mixing at the solution level can address all these things. You know, you may be able to do the synthesis, or you may be able to fabricate the materials at a fairly low temperature, even at a room temperature, and you can finally control the crystallite size. You can do so many, you know, many controls are in your hands when you're going to start from a solution and then end up in a solid, not from a solid, end up in a solid. Okay, so this is the thumb rule with which we keep working. Since 2005, I have been doing this aspect only. And you know, this reaction profiles we have seen in many chemistry classes. It would be there. I mean, there is a reactant side, there is a product side, and I have purposefully included the thermodynamical parameter here, that is the delta H, right? So we have some reactions called as exothermic reactions. That means the energy is released during the reaction, and it has a very large activation energy, and the reaction is very slow. Okay, and exothermic but favored large K, that is large EA, but slow, stable, slow reaction, stable intermediate. That is the second one is that. And if you see here, you can capture the intermediate very nicely. You know, there is an intermediate. I do have a pointer. I mean, that's okay. There is an intermediate in the second one. There is a valley there. Okay, so the valley you can capture very easily. And the third one is the endothermic one. Endothermic is extremely fast reaction. So you have to design reactions in which the reaction conversion from the reaction to the reactant to the product should be a endothermic. Then you can have a very fast reaction. Or if you want to capture the intermediates, what do you call them as intermediate? The intermediates are nothing but a kinetically stable products. They are going to be dependent only based on time. If you put more time, it will then convert into a thermodynamically stable phase. So we are interested only in capturing the kinetically stable products, because kinetically stable products can give a lot of interesting properties, which can be called as a multifunctional aspects of these materials. Okay, let me take the example of polymorphs. I mean, polymorphism, all of you would have studied, and at least you would have heard, right? Polymorphism. What is a polymorphism? Is the same chemical formula, but different structural arrangement, right? And the example which I am going to take is titania, that is TiO2. As I told you, titania is put in our dials also, in the wristwatches, as a white background. That is the purest white. White, if you go by the color index, that is the purest form, white. So titanium, TiO2, can exist in three different structural arrangements. One, oh, thank you. Okay, so titanium exists in three different polymorphic arrangements. One is the anatase, and another is a rutile, and another is brochite. Okay, in this, whatever the terminology still now I have introduced to you, it is all present here. That means it is a metastable form. That means it is a kinetically stable one. And it is an open structure. What do you mean by open structure? Open structure means you have lot of empty spaces. If you have lot of empty spaces, you can use it for sensing so many other things, wherein you can load the molecules wherever the vacant spaces are going to be there. Okay, and this is a thermodynamically stable form. That means, when you heat it, then you are going to always get rutile as the thermodynamically stable form, and it is a very, very compact structure. So rutile is of no consequence to any of our major applications. And then bruchite is also a metastable form, and I have given some things here, which is the optical absorption edge. That is the band gap of 3.2 electron volt, which annotation is showing, and 3 electron volt and 3.4 electron volts. These are all more or less a broad, wide band gap semiconductors. So semiconductors are quite useful because, semiconductors are, we have been working on optically conducting and, optically transparent and electrically conducting solids. That means the electrical conductivity should also be there, and they should be active in the UV visible region also. So they are quite useful in many optoelectronics. And that is one of the things that we have been working. So polymers of titanium, there are 3. And I am going to take one simple approach. We were interested to make this titanium dioxide in different colors because, our group has been working on the optical properties of solids for more than 18 years now in University of Delhi. So we don't like the titanium to remain as white. We want to make it in different shades, different colors. How to do that? How to do that? So obviously you have to, you can't use the thermodynamically stable approach. You cannot take a titanium metal and then oxidize it to form titanium dioxide. So one of the ways of introducing color to the titanium dioxide is to create some defects or is to create some color centers there. Okay, so if you can make some vacancies or defects there, and if you can make those color centers, then those titanium dioxide, they are not going to be as white. They are going to exhibit a different color. So one of the approach that we took, see, in all these things, we have handled only one precursor. So the theme is we will take only one starting material, but we will end up in different colors of titanium dioxide. So that is how we have done. So what is a synthetic approach for any advanced functional material or any functional material? What is the starting point? Starting point is a synthesis. Starting point is a preparation. Starting point, you can call it in, engineers can call it as fabrication, but scientists always call it as synthesis. So synthesis is very important. So what we have done is we have taken a titanium metal powder, dissolved it in hydrochloric acid, and this is a very famous ligand, EDTA. EDTA, we have been taught in +2 also. And EDTA is quite useful as a, medicinal use because, EDTA is used to treat thallium poisonings too, in human beings. So if you have a cadmium poisoning, if you have a thallium poisoning, if you have, so this EDTA is regularly, it is biocompatible one. It is a polyamino carboxylate. So that means carbon, hydrogen, nitrogen, oxygen, they are all compatible to your body. And this ligand is also compatible. And therefore, this can be used in bio-related things also, which we will be seeing little later. So titanium metal powder, and then we have just a complex state with the EDTA, 1:1 complex. That means one titanium and one EDTA, as simple as that. And then what we have tried to do is, we have tried to remove this ligand, remove the ligand in a very graded manner. And what we have finally got is a black colored TiO2, okay? But if you are making something, then, you have to prove also. I mean, in science, you have to prove. And this is the precursor. The precursor is amorphous in nature. There are no diffraction peaks for the complex because it is consisting of weakly diffracting elements. What are all the weakly diffracting is carbon, hydrogen, nitrogen, oxygen. There is the only one heavily scattering atom, X-ray scattering atom, that is titanium. And therefore, you will not see a diffraction pattern for the precursor. And we then take it and we wanted to know at what temperature we will be getting an oxide from that. And therefore, we did a TGA of it. There is a thermogravimetric analysis. That means you keep rising the temperature, keep measuring the weight. And at a particular where it is reaching a plateau, then we pick up that temperature and then we will calcine the complexes. That means we will be heating the complexes in that temperature. So this is a FTIR spectrum to make sure that it is not remaining as a free EDTA, it is bound with the metal ions. Okay, so these are all certain proofs that we have to give. Okay, now that after heating the complex, at a particular temperature, I mean around 600 degrees Celsius, not in oxygen atmosphere, but in an oxygen poor atmosphere. That means, you pass argon or nitrogen, highly purified argon or nitrogen, they don't have oxygen to supply. So what we are interested to do is, all of you must be knowing, titanium can exhibit variable valence oxidation states because it is the transition metal ion. What do you call it as a transition metal ion? It can capable of exhibiting different oxidation states. TiO2 is white in color, but TiO is black in color. So TiO is titanium is +2 oxidation state. TiO2, titanium is +4 oxidation state. In addition to that, titanium can also exhibit +3 oxidation state. So +2, +3, +4. But the most stable oxidation state is +4. And therefore, what we were trying to do was, can we introduce the reduction, some amount of titanium to go to titanium 2+, and then titanium 2+ and titanium 4+ coexisting in titania, then you will get a black color. And that is the reason that we could make a black color anatase. This black color anatase, we wanted to prove that it is really the oxygen poor environment that it is giving rise to this black color. We took the sample and then heated it in flowing oxygen. That means it has taken enough oxygens and therefore it has given a white colored anatase. So there is no structural change that is occurring between these two samples. That means the black color is inherent to the sample, that because of these procedures that we have followed. These are all additional proofs that one needs to give that, yes, I am trying to make my sample microscopically pure also. I mean, it's not that macroscopically pure substances are enough for technical applications or technological devices making. You have to make sure even under microscopic level, they are all pure. So these are all certain evidences that we have sought that titanium, black titanium dioxide that we have got is microscopically pure also. And this is you can imagine now, the band gap, which was around 3 electron volt, has come down to 1.7 electron volt. That means we have made a wide band gap semiconductor into a metallic compound. That means this band gap, it is reducing enormously from 3.3 to 1.7 electron volt. So this is called as the talk plot. That means you can find out the band gap from the absorption spectrum, and absorbance, you can convert it into photon energy and you get this. Okay. Now, one more technique which we have done to prove that our sample is what kind of a local symmetry that it is having, or what is a local structure that it is having, is the Raman spectroscopy. Raman spectroscopy tells you, I mean, powder X-ray diffraction tells you the global symmetry. But if you want to understand something that is happening locally, then you have to use the Raman spectroscopy. So in the Raman spectrum, we got some very interesting thing that in addition to the peaks that are due to the anatase TiO2, we are also getting some bands due to the graphitic carbon. That means the G band and the D band. There's a graphitic band and the D band that also comes along with that. So what could be the origin? Why we are able to make an in situ composite between the graphite and the black titania? Then we thought about it, and there is a ethylene backbone, ethylene diamine tetraacetic acid. So there is a ethylene backbone. If you want to make graphite, you know how to make graphite, or industrially how graphites are being made. You have to take acetylene, CH triple bond CH, and you have to remove the hydrogens. Okay. And if you remove the hydrogens at a high temperature, then you can make graphites. Okay. Our report is the first report wherein we have shown you don't need acetylene because acetylene handling is extremely dangerous. Acetylene cannot be handled very easily. For that, a special training should be there. Ethylenes, substituted ethylenes can also be converted into the graphite. So that is one of the important observations from this study, and the reviewers appreciated that. And we have to prove that the titanium is present in the lower oxidation states other than titanium 4+. So titanium 4+ is D0, but if you have titanium in the lower oxidation states, they are all going to have some electrons, and those electrons are going to be paramagnetic because they are not going to be paired up. And therefore, this is a EPR technique in which we proved that there is a titanium 3+ in addition to titanium 4+. Of course, this, one of the advantages of coming as a more or less a pre-final speaker is you would have been introduced almost all the aspects of all the things, and I will come like a dessert, last. And people will always look for the dessert. Dessert should be good. Whether the food is good or not, the dessert should be always good. And therefore, I wanted to, and it protects our time also, because most of the things the audience would have been introduced, and we can straight away go to the content what we have to present, right? So this is the X-ray photoelectron spectroscopic analysis. This is just to prove that the titanium is existing in mixed oxidation states. And we have proved this as a good photocatalyst for the degradation of this complex dye molecule, that is rhodamine 6G. So this is one of the function right now. And then we have taken a colorless contaminant, which is present in our plastic bottles, all our water bottles. Nobody is paying attention to this, but this BPA is there. And this is slowly getting into our body also. Even we have started accumulating microplastics. So this also we try to make sure that in the presence of a solar simulator, all these things are getting completely dissociated into smaller fragments and becomes a colorless, becomes a harmless entity. So we have also shown one more dye molecule, which is eosin yellow. Why we have to show all these things is textile industry, cosmetics industry, they throw a lot of these dye molecules outside without proper treatment, effluent treatment into the water resources. And therefore, it is very, very important, at least at the effluent treatment level, we should be using some of this catalyst or the photocatalyst to make sure that they become less harmful before they enter the water body, main water bodies. So this work has been published in Material Research Bulletin in 2020. This is the one black titania graphitic carbon nanocomposite from a single source precursor, and this interaction with colored and colorless contaminants. So if you want to know more about this work, you can visit this paper. The second one, the same titanium EDTA complex. I have not varied anything. We have not gone for anything else because the same complex what we have done earlier was heat it in argon at a very low temperature. Second one, we have just taken it and we have treated it hydrothermally. That means, you have just dissociated that complex using pressurized water. Okay, pressurized water medium. Then what is that is happening? That was an interesting scenario. So therefore, we wanted to know, and I think my student has already made the banner, everything in this slide as yellow. So that means, that is indication that you are going to get a yellow color titania. Okay. And that is the product that we got. And again, the structure is not different. It is the same anatase, which was white in color. We could make black in color. Now we have made it in yellow color. And these are all some of the proofs which we have to give. And in this, there is no graphite. Because, see, you are not giving, you can polymerize the ethylene backbone only by thermal treatment. So thermal induced polymerization happens. But here we are doing the reactions in aqueous medium, and that too under a closed vessel. That means there is no possibility of any ethylene getting polymerized. So this is so these are all the routine proofs which we have to give. So this also had a mixed oxidation state of titanium, and what it indirectly indicates is, if you are going to vary the amount of the lower valent titanium, you can end up in very good coloration, different coloration of titanium dioxide. Okay. And this again has been investigated as a visible light photocatalyst. That means the yellow color falls in the visible region, and therefore you can use the visible portion of the solar spectrum to prove that it is acting like a catalyst. And we have demonstrated this for a variety of dyes, and colorless and colored as well as colorless contaminants. And we have also investigated what is the reaction mechanism. I mean, what is the reactive oxygen species that is possible in these experiments, that is hydroxy radical, OH radical, that is promoting this degradation. Okay, and we have tried to find out what are all the end products that are forming after the complete mineralization of these dyes. We are getting salicylaldehyde 98%, phenol 0.3, hydroquinone 0.8, and coumarin 0.4. So these are all some of the organic molecules. You don't have to worry about this. More information you can find in this paper, that is visible light photocatalysis promoted by homogeneously doped. That means we are replacing some amount of oxygen with nitrogen and carbon. And because of that heterovalent anion doping, you are able to reduce the titanium 4+ to 3+ and 2+. And because of that, we are introducing the color. Okay. Next example which I would be taking is, we have made nano crystals of anatase, which are functionalized with EDTA and diol. That means, you must be knowing all these formulations, pharmaceutical formulations, they are made in propylene glycol. Okay, that is why they are very thick, viscous liquids. So this ethylene diamine tetraacetic acid is also biocompatible. Diols, propylene glycol, ethylene glycol, they are also biocompatible. And our intention is to actually dive into its bio applications, but that takes a lot of time. And before that, as a chemist, we cannot wait. We have to publish certain things. So the biology related work is going on, but the chemistry related work is published, and therefore I will present that with you. But what we have tried to do in this is the same titanium EDTA complex I have taken. I have just changed the medium from water to propylene glycol. And this is a closed vessel that I'm using. And I'm having the color of the sample now is changing to red. Okay. And we have tried to use this to remove the thiophene molecules. I mean, what is the role of thiophene molecules? Thiophene molecules have to be removed because all your petroleum products, they contain lot of sulfur-based compounds, out of which thiophene is the major one. And therefore, people have been working on how to, at least the petrochemical industries, they work on how to remove this thiophene efficiently. Okay, so what we have tried to do is we could adsorb out all these thiophene molecules using this, EDTA diol functionalized titanium, anatase titanium dioxide nanoparticles. So this is a red color that we have got. So the same anatase, same titanium dioxide, but it is now red in color. And these are all the additional proofs, I mean, microscopy proofs that one needs to give. And you can also do elemental analysis. Elemental analysis tells that titanium, carbon, oxygen, nitrogen is there. And how we found out the surface functionality of this compound. That means you just simply run one IR spectrum, you will see the surface is decorated with the ethylene propylene glycol moiety. So these are all the additional proofs which we have given through an IR and NMR. And how the band gap is varying. The band gap is 2.2 electron volts. And the Raman, we are not seeing any graphitic carbon because we are doing it under closed vessel and under non-aqueous solvent. And therefore, we are not giving any thermal energy to get it polymerized. Okay. And this is the EPR to prove that titanium is present in the lower valent oxidation states. And this is the XPS, which we have done, that whether seriously you are having the surface that is functionalized with propylene glycol or not. So if you want to, XPS is a surface technique. So if anything is decorated on the surface, if anything is adsorbed on the surface, if you have to prove that, then you have to do X-ray photoelectron spectroscopy. So we have proved and we have shown that it is all decorated. The nanoparticles are decorated with the propylene glycol moiety. And the titanium is also mixed oxidation state. That means a lower valent titanium is also there and higher valent is also there. And if you see, if something is decorated or coated with a decomposable moiety, propylene glycol is a decomposable moiety. And in the thermogram, it is losing weight and it is coming down. And if you see here, it is very interesting, the anatase, when you are removing the solvent, when you are removing the coating that is nicely decorated on the surface, then you do see the formation of the thermodynamically stable rutile phase along with the anatase. That is, so this weight loss is very typical of esters. Esters, what is the things. So this is the product obtained after calcining the red anatase or red titania. So we have characterized this. And now if you see very carefully, whenever you're using temperature, at 400 degrees Celsius, then you are again seeing the graphitic bond. So we are pretty sure now that this ethylene backbone of ethylene diamine tetraacetic acid can be very nicely, safely converted into a graphite. So that is a very, very important thing which we have given it to the scientific community. And this is desulfurization of thiophene is a very important topic in petrochemical industries. And therefore, this we have tried to do because, we are having alcohol on the outside. That means, we are having hydroxide units on the surface of the nanoparticles, and therefore they can be very easily taken, they can attract the sulfur molecules towards themselves. And that is the thing that we proved in this. And these are all some of the, batch experiment results, which we have done, how much we can remove and all those things. It is practically being used in Hindustan Petroleum now. They have taken it up, this work, and they are working on it. And these are all some of the proofs that we have to give. And we have also tried to find out whether sulfur has been adsorbed on the surface or not. We have done the XPS analysis. You can see that the sulfur oxygen moiety is also there, and the SO4 is there, SH is also there. So that means the sulfur has been effectively absorbed from the solutions, and it is sitting on the surface of the polyol decorated titanium. So this is additional proof that we have given through NMR, and this has been published in Langmuir. Okay. And if you want more information, please go through this publication. You will get more. And this is the third and last example which I will be taking. Okay. Zirconium oxide, ZrO2 is a very, very technologically, very, very advanced material. I hope all of you know that. Zirconium is used in your automobiles also, okay, as an exhaust cleaner, okay. And bismuth oxide is a high oxide ion conductor. And zirconium, there are many polymorphs which are possible, cubic, tetragonal, monoclinic, etc. Similarly, bismuth oxide, you know, a lot of things are known, alpha, beta, gamma, delta, etc. So it is extremely challenging to react these two to get one pure compound, okay? So let me put it in that much simplest fashion. So we were interested to make zirconium is +4 oxidation state, bismuth is +3 oxidation state. If you are replacing like your you know, N-type, P-type, if you are replacing some amount of zirconium with bismuth, then you are going to create oxygen vacancy there. Then that oxygen vacancy can be used for oxide ion conductivity. So that is the aim and that is a purpose. And here again, what we have done is we have just simply captured both the metal ions using EDTA. Okay. So bismuth 3+ and zirconium 4+, they both form a complex, 1:1 complex with EDTA. So we have made that. We have done the rest of the characterization. We have done a thermogram, and we have calcined it at a low temperature of 600 degrees Celsius, wherein we are getting you know, compound which is a pyrochlore, which is for the first time we have proved that. And this is additional one. I mean, you know, the flower-like morphology is present for this sample, and microscopically they are pure, and the elemental ratio between zirconium and bismuth is more or less 1:1. And we have characterized its local coordinations using Raman spectroscopy. And it has a band gap of 2 electron volt. That means it can be very well used in the visible range. Okay. And we have shown the luminescence from this solid, which is bismuth, basically coming from bismuth 3+. And this has a reasonably good surface area. And therefore we have, so we have seen its oxide ion conductivity measurements. It shows excellent oxide ion conductivity. That means oxygen vacancy is there, and that oxygen vacancy is mobile. Okay. So this is useful in solid oxide fuel cells, SOFCs. Okay. When you use a solid electrolyte, it has to conduct oxide frequencies. We have done a bunch of other functions. You know, it can be used as a catalyst. It is used as an oxide ion conductor. That means it is a multifunctional material. You have shown 2 different functions, 3 different functions. So nitrophenol to aminophenol, where is the nitrophenol coming from? Nitrophenol is coming from pharmaceutical industries, you know, and nitrophenol is very, very dangerous. Okay. So we have to convert them into aminophenol before we let the things reach the water bodies. So that is what we are trying to do. And we have also converted a bunch of nitro groups into amino groups. That means the oxygen vacancies can very well be used for reduction reactions as well as oxide ion conductivity. I mean, it shows both the functions, you know, that is oxide ion conductor as well as it is useful for a reduction of substrates. We have also tried to do chromium 6 to chromium 3. This is also important conversion because chromium 6 is effluent coming from leather industries. So we have to make sure that to get converted, you know, anything which is in a higher oxidation state is very, very dangerous to our body. So we should make sure that it is reduced to the lowest oxidation state possible. before letting it to mix with the water bodies. So this is what we have tried to do. Chromium 6, we try to reduce it to chromium 3 using these samples. So this is the paper. If you want to know more about these aspects, please go through this paper. And if you have any queries, I'm ready to answer. Thank you once again, the organizers, for giving me this wonderful opportunity to interact with the audience. Thank you.
Thank you so much, sir, for your wonderful talk on the fascinating material and talking about the fundamental of the material science. And we have seen like how your synthetic approach is we are able to get different color titanium oxide and how we can use them for visible light photocatalysis. And this is very important because as far as I know, titanium oxide undergo catalytic action under the UV light. So if we can do photocatalysis under visible light, that is a great thing. And thank you so much, sir. And it is really an honor to have my professor, teacher, guru from Department of Chemistry, University of Delhi. And he came here in a very short notice and time. And thank you so much, sir, for sparing your time.
Thank you. It's my pleasure.
Yeah, and now the session is open for questions.
Yeah, that was a great talk, sir. So I was just wondering whether, I mean, you started out trying to make titanium dioxide nanoparticles with EDTA as a ligand and removing the ligand, and by serendipity, you ended up with graphite, or you started up that way?
I have to accept the truth. It is serendipity.
Yeah.
Okay. It is accidental. I never had that aim.
Yeah.
You know, our aim was to make different colors of titanium, but actually that is a serendipity. I'm accepting.
Yeah. So yeah, because the reaction scheme, it points out that is what you were trying to aim for. But I mean, it is very interesting. But did you try, now manipulating the band gap by that method? Because you had just one of that with high temperature, rest for all hydrothermal. So could you manipulate the band gap by the high temperature method?
One can do that. That's a good question. And due to, I think, this Corona and COVID, the students are not available. And students with a lot of patience are required.
Yeah.
If you have to do good science, you have to have a lot of patience. I'm not anything against the younger generation. Please don't misquote me. But the younger generation are appearing to be more impatient. We have all been patiently doing certain things, and patience and endurance will give certain things. That's a very good suggestion. Yes, we have not yet attempted towards that, because the students are dying hard for a degree. So they say, I want to get the degree, so I had to stop somewhere.
The second question is, you said, sir, the XPS about the sulfur, but XPS is technically, let's say 8 nanometers. So I would suggest you try LEIS, low energy ion scattering. So that, you can actually.
I totally agree with that.
Yeah.
XPS is not the solution. XPS is not the solution because XPS has its own inherent problems. The vacuum, ultra-high vacuum that is being created in XPS can also reduce the metal ions. Yeah. And as you said, the depth is 8 nanometer. We are trying to prove through other methods also, like cyclic voltammetry and other electrochemical means also we are trying to do. But reviewers, they like XPS results.
Yeah, but then there are two different
because they
things.
have to promote their machines.
Yeah. So I think when you do an XPS, sir, next time, please do an UPS too on the same instrument.
Yeah.
So that
we
will
try to do UPS. And there is one more technique. I hope all of you know about it. Electron energy loss spectroscopy.
That is what I said, LEIS. That is what I said, sir, LEIS. So that will give
yields is the ultimate thing which can give us the,
Yeah.
But this kind of specialized, I mean, I'm very sorry to say, I don't know whether you people have a microscope here, TEM. Okay. Even we, I'm very sorry. In our country, there are no good microscopists.
Well, yeah. Well, 3 at IIT are down, IIT Delhi, and I think, yeah.
Yeah, I mean, the problem is I know what I'm looking for, but I'm not allowed to go near the microscope. And I tell the operator, this is what you're supposed to look for. He says, sir, I have tried. And you have to sit in the dark room for a long hour.
Sir, I can arrange at University of Michigan, Ann Arbor, if you want. You know, they have a 300.
Thank you.
MBBS.
Thanks a
Yeah,
lot.
so
Thank you very
that is one thing. The third thing you said, you know, the surface. So another experiment you can do is the surface oxygen exchange. So for the SOFCs, if you have a mass spec with you, you can actually dose with labeled oxygen, right? So O18, if you dose, you can monitor the formation of the cross product.
Okay.
Like, you understand what I'm talking about, sir,
I
right?
understood.
So,
Kinetic isotope effect.
right. So that will give you insights on this, on the system more.
Thank you. Thank you very much for the suggestions. And if you can help us with more, see, I have handled microscope with my own hands when I did my PhD. Electron microscopes I have handled. Only thing is nowadays it is mouse controlled. Earlier it was not mouse controlled. I mean,
yeah, we had to adjust the, you know, all the apertures ourselves.
Yeah.
Nowadays it's all automatic. Yeah.
So the problem is a microscopist should also know crystallography, but he is not equipped. And they say this is the maximum we can give. And okay, that costs a huge amount of money also.
Because some of the fringe widths and all, you know, they could have been better.
Yeah, I totally agree and understand, but I don't know whether it is a third world country problem or I don't know, but there is some problem with the, kind of characterization that we are doing here.
Thank you, sir. Thank you.
Thank you, sir, for coming our university. And this is second time you are visiting us.
I know.
So I hope you recall this. Thanks for a great talk.
Yeah, one of my students was a faculty.
Pooja Rawat, Dr. Pooja Rawat. Yeah.
Pooja Rawat was a faculty here.
Yeah.
And that time she pulled me. This time Neeru pulled me.
So it's our pleasure that you accepted our invitation and just came to just
no issue.
For addressing in this conference.
I don't go out frequently.
Yeah.
Since
but
Neeru
your work was excellent and you did a great job, sir. It is actually just a contribution for society that EDTA say you are generating that type of material, and actual research is by serendipity. That's what I guess.
Yeah.
So
but we have to be honest in accepting.
Yeah. And you are great, sir. You accepted it. Thank you very much. Thank you.
Hello, sir. It's a nice work, whatever you have presented. I am a biochemist and I want to ask a general simple question. It's simple for chemists and physicists.
Please.
Most of the nanoparticle guys, they works on dye-degradation, right?
Yeah.
And dye-degradation for industrial effluents, possibly, right? And we are adding some nanoparticle like TiO2 and those things in that one. So we are adding something else in the water. That also creates some later problems. So whether we are worried about that one also, like dye is degraded, we are not worried about what are the products of dye is there, and we are also adding some harmful toxic metals.
Yeah, that is a very good question. The theme is, are we not generating a secondary waste? You are trying to address the primary waste, but through that you are generating a secondary waste. That is your question. I agree, but at least only European Commission has announced that 2 years back, titanium dioxide is also harmful. Till such a point, all over the world, everybody thought titanium dioxide is very, very inert and it is it is not lethal. I mean, it is not toxic to your body. And therefore, people have churned out a lot of, this kind of studies. But if you seriously look into all these things, titanium is a any metal, if it is present in excess in your body, is a problem. Whether it is copper, whether it is iron, whether it is selenium, whether it is magnesium, anything, that is why they are called as a micronutrients.
Iron, those are generally present in minute amounts in different enzymes and prosthetic groups. But titanium, I haven't seen titanium in any of enzymes or proteins in our
That's
body
true.
applied.
That is true. That is why we have a lot of implants based on titanium screws. So thinking that it is not going to react with our biosystems, and it is going to be more or less toxic, non-toxic. But given the scenario that now that European Union has declared that, I mean, sooner or later, I think all other unions will also declare that yes, it is titanium dioxide is not biocompatible. So like this, we should try. I mean, these are all simple proof of concepts to maybe motivate the younger researchers that you can do all these things, you can do these things. But if you really go into the industry, and when you are going to turn it into a technology, that has to be handled in a different way, different level. And in that, this secondary waste generation should be addressed. I agree with you.
Thank you, sir. Thank you for the wonderful talk.
Thank you.
Now I request Professor Atul Thakur to present the memento to Professor R. Nagarajan.
So I'm also calling Dr. Seema, Dr. Molly, Dr. Ambika, come.
Thank you, sir. Thank you, ma'am.
Dr. Prasanna, please.
Thank you, sir. Yeah, please.
I'm happy he gave me a cup.
Empty.
No,
Empty
the
cup.
cup is never empty because love is always abstract. Thank you. Work with love. Work with love is preparing a delicious cake. Otherwise, it is a rotten bread. Work with love is preparing a delicious grape juice. Otherwise, it is a rotten wine, told by Khalil Gibran. Now, Natarajan spoke about chemistry. I feel that he is my brother. We are Raj brothers. He is Nataraj, I am Prasanna Raj.
Thank you so much, sir. So now we proceed to our next session. I am delighted to introduce our next speaker, Dr. Deepshikha Rathod from Amity University, Jaipur, Rajasthan. She has expertise in synthesis and characterization of various nanoferrites, nanocomposites, and fabrication of gas sensing devices using nanomaterials. Her current research interest involves nanomagnetic materials, nanocomposite. Okay. Yeah, so I welcome Dr. Deepshikha Rathod. Please share your ideas about nanoferrite properties and application. Welcome, ma'am.
Yeah, thank you so much. Good afternoon, everyone. So quickly we will go ahead, but before starting, I would like to thank to Professor Atul Thakur sir to invite me. I have chosen actually nanoferates because it's a very favorite subject of Atul Thakur sir. So my title is nanoferates, properties and application. If anyone wants to discuss in between, definitely you can ask, because the title I have chosen for students only. So we are going to discuss here the basic nanoferates, experimental techniques, some properties and applications, and also the gas sensor, whatever I have designed, and then types of gas sensor, fabrication of gas sensor, how we can just fabricate, and then mechanism, whatever patent and publications and projects I have done till now, and then summary. So before starting the nanofarad, we should know about the structure. And here, as nanofarad, whatever we are synthesizing and doing everything in our lab, we are using the spinel. There are two types of spinel farads, normal spinel and inverse spinel. So what is the difference between both? Firstly, we will see, and then we will take the particular properties on the basis of these farads, these normal and spinel both. So in the divalent, basically in the normal spinel farad, the divalent metal ions possess the tetrahedral side, and the trivalent metal ions, B ion as it is written here, possess the octahedral side. But in the inverse spinel structure, the B trivalent metal ions possess both half-half part in the tetrahedral side, and also it goes in the octahedral side. And divalent metal ion possess the octahedral side. So in this case, basically, all tetrahedral and the octahedral sides arrange alternatively, and we get the complete structure. And you are able to see it is not simple cubic. So this structure always plays very important role in different properties, and also we can utilize in different applications. So basically, why we are focusing on the nano? Why we are not we are not working on the bulk ferrite? Because our target is to enhance the properties. So as below 15 nanometer, nanoferads gives us the better nanomagnetism, which gives the broad range of magnetic behavior, which we will see in our results, and large magnetic moment. And also below 15 nanometer, it comes in the single domain. So it also gives us the super paramagnetic behavior. Now we are going to discuss the experimental techniques. So synthesis technique, basically here I am following only the chemical co-precipitation method, in which the important factor, the growth process variable, where I have varied the reaction temperature and the molar concentration of reagents. I followed in this talk basically the XRD, VSM, impedance analyzer, AFM, FESEM, Raman, and FTIR spectroscopy. So in the co-precipitation method, basically I have utilized the two precursors for divalent and trivalent metal ions, and I used here the chlorine precursor, and then mix in the alkaline mixture, NaOH, and then string, and then after a particular time, it comes in the precipitation nanoferrite form. So here basically sintering process I am not following, so which we will just discuss. So I am following here the cobalt ferrite and nickel zinc ferrite combination. So cobalt ferrite nanoparticles were synthesized at different concentration, 1%, 5%, and 10%. And then temperature, I have taken the 10 degrees centigrade, 25 degrees centigrade, 55 degrees centigrade, and 75 degrees centigrade. And then set of this this particular set of this temperature I have taken in different percent concentration. I have seen here one interesting thing that at 1% concentration and the initial temperature, there is no any peak. There is no any XRD peak coming. And then the after increasing the reaction temperature, the peak started to come. And then as the concentration increasing, the peak intensity also increasing and the width of the peak decreasing. So interesting thing is that as what is the minimum concentration you can utilize without sintering, you can find out the nanoferrites. Same concentration and temperature I have utilized, at which I am getting very small size of the ferrite for synthesizing the nickel zinc ferrite in the combination. And I also get here the very small particle size, which we will discuss in the table. And here you are able to see as concentration increasing, the size of the cobalt ferrite nanoparticles increasing, and also it is coming in the crystalline form without any sintering process. So this is the first thing, how we have to control the reaction temperature, and then we can just control the concentration of the reagent, whatever we are taking in our reaction. So without using any kind of surfactant, pure ferrite nanoparticles we can synthesize with the help of controlling the particular parameters. And after XRD, as we always find the conformation, so I have done the rate wheel refinement for all nanoparticles. And then we got the parameters in a perfect form as better goodness of fitting and chi-square value with the particular space group, which we have taken for the refinement. And all nanoferrites came in the cubic form. And now furthermore confirmation, I followed the FESEM and atomic force microscopy for finding the images. And I also got in this form the 5.8 nanometer image is giving very small cubes. And 28.6 nanometer is giving a little bit bigger cube. And also we can just find out the particle size with the help of this. And with the help of atomic force microscopy images, we can also see this is also in cubic form. So it is also confirming our sample is in the cubic form, and the particular size is coming near by the XRD results. And now we are just performing here the magnetic properties with the help of vibrating sample magnetometer for all size of the particles. Two particles we have just escaped because those were the amorphous. So here I have taken the just magnetic we applied the magnetic field, and then we have seen here these as saturation magnetization increases with the particle size, and then remanent magnetization also increasing with particle size. And this we can just correlate with our other properties. And here interesting thing, as particle size is varying, then the blocking temperature with the help of field cooling and zero field cooling curve, we are able to find out. So as the size is decreasing, the blocking temperature is decreasing in this curve, you are able to find out. And here for particular particle, we are able to see at different magnetic field, we are finding the different blocking temperature. And with the help of blocking temperature also, we can just calculate the size of the particle. But before discussing the blocking temperature particle size, we will discuss the same thing for the nickel zinc ferrite. Whatever 3 samples we have synthesized. In this, the nickel ferrite basically follows the inverse spinel structure. And the zinc ferrite possess the normal spinel structure. But if we are mixing the 50-50% both, we are finding the saturation magnetization increases. This property is very interesting, and we can utilize this property in the different applications as we are going to discuss in our next slides. And also here the blocking temperature, we can just calculate with the help of zero field cooling and field cooling curve. Now next, with the help of a blocking temperature for the cobalt ferrite nanoparticles, I have calculated the volume of the particle, and also I got the result, which is almost similar with the XRD results. And it takes it gives our very good information. And now next, the dielectric properties also I tried to find out how it is varying with the particular particle size. And I got here, as the size increases, the dielectric permittivity also increases. Dielectric permittivity decreases as size decreases, the dielectric constant increases, meaning we can just find out very good dielectric material with decreasing the particle size, as we are finding in the cobalt ferrite nanoparticles. Same thing will happen for other ferrite nanoparticles, as I have seen. I have synthesized different types of nanoferrites, and the loss tangent also decreasing on decreasing the size of the particle. So same interesting feature, whatever we were finding in the nickel zinc ferrite, 50-50%. Here the dielectric constant for the nickel ferrite and dielectric constant for the zinc ferrite is little bit lesser than the combination of both. So we can just enhance the property after mixing the two ferrites during the synthesis process. So this nickel zinc ferrite 50-50% is giving the very good dielectric property. Then dielectric loss also we can just find. And with the help of the dielectric properties, we can calculate the activation energy of the material, and then that activation energy we can utilize to understand the gas sensing properties and also different properties. So activation energy were calculated with the help of this S parameter and also the conductivity, and we received the particular value of the activation energy. And here with the help of that particular activation energy, we are able to confirm the particular phenomena which is happening in the sensing process, which we will discuss in our next few slides. So also the Raman spectroscopy performed for the different size of the cobalt ferrite nanoparticles, and we received here the 5 Raman active modes, and those modes are for the metal oxides bonds. And also we have followed the FTIR spectroscopy, and here also we are following we are finding here the different bands. First these bands are for the tetrahedral site, and remaining 2 for the octahedral site, but last fourth number band is not in our range. So we are also confirming our the formation of the cobalt ferrite nanoparticles with the help of this FTIR spectroscopy. And then now we are coming on the application, and which I am taking here the gas sensor, as I am working on the gas sensor. So first interesting thing, large number of gas sensors are available in the market as the technology has been enhanced, and but still we need the sensor. Why? Because we want to prevent the different kinds of tragedy as happened in our country in 1984 Bhopal Union Carbide gas tragedy. And after this particular year, we have already established large number of laboratories, and also large number of technology came, and in which the sensors basically designing with the help of metal oxides, different kinds of metal oxides as shown here, and also the carbon nanotubes being used, 2D materials, graphenes, and different kinds of conducting polymers are being used in the gas sensing technology. And large number of gas sensors are also available, has been installed in our laboratories. Is still in 2020, during the corona time in Visakhapatnam, the styrene gas has been released, and it came in the small tragedy form. So why these kinds of tragedies are happening, as we have very good technology. So this is very big thing to realize. So meaning is that we need some more different kinds of sensors, not only to inform, also to stop. So to stop the tragedy. So how we can just enhance the efficiency of the sensor in terms of different parameters. We have to enhance the sensitivity, selectivity, precision, accuracy, durability, response recovery time, repeatability also. So with the help of all those parameters, we can just enhance the sensitivity. So as material scientist, we can just do something more in terms of the sensor. So these sensing parameters depends upon the particle size of the particular material which we are using, crystallite size, grain boundary, and interfaces, also defects present in the material, imperfection and strain generated in nanocomposites, operating temperature and time, type of the gases which we are testing, and also the concentration of gases. So all these we can just take in our consideration, and then we can just develop the very good efficient sensor. So how we can just calculate our response in terms of the sensitivity. So if we are taking the change in the resistance, so firstly resistance in air we have to measure, and then resistance in the gas atmosphere. If the resistance in the gas atmosphere is greater, then obviously we have to divide it, and then we can calculate the percent sensitivity in the response form. And also if the resistance of the resistance in the air of the device is greater, then obviously we have to divide it, and then we can calculate the correct percent sensitivity. So this is the simple formula. If any student want to calculate the sensitivity, they can just utilize these both formula. And how we can just take the ppm, parts per million, because everywhere the particular meter is not available. So if you are doing your experiment in your laboratory, then you can just calculate the ppm with the help of this formula. So if in this case, particularly the standard chemist ppm, we always take 1000 ppm, and the quantity for quantity of gas, if we are taking it is 1 ml, with the help of syringe you can take. And then if the volume of the chamber is 500 ml, which you can just measure what is the correct volume of your chamber, and then standard ppm which you want to calculate, you can just use here. So in this case, whatever values are written here, you can find out the x equal to 2 ppm. So basically the simple experiment you can do, you can run in your laboratory, and you can find out the sensitivity of your material. So type of gas sensing devices you can just follow. Simple capacitive device also you can follow, whatever I have also followed in initial time before 13 years. But nowadays I have some more technology. So but in initial time you can follow the capacitive device, and hope so you know how we have to design the capacitive device. And on the thin film you can just make the parallel conducting electrodes. And if you have the vacuum evacuated coating unit, then obviously you can also design your you can design the electrodes on your sensor in the fingers form. And this in my PhD, I have just designed this kind of device. And nowadays I'm working on the 2D printing technology, in which I'm using the inkjet printer, and then using the particular nanoparticles. I am designing, I'm fabricating the ink of the nanoparticle, and then filling the ink in the particular modified inkjet printer, and then got the printed sensor. And then also the electrode have been designed, and that sensor is now capable to sense the different kinds of gases, which I have designed in my project. And so I have also established different types of gas sensing facility in different times. So during my PhD time, I tried the gas sensor, gas sensing technology using the U-shaped tube. And then in during before 10 years, I just tried because I left the Barkatullah University and I joined the NIIT University. Then I tried the simple experiment in the box, a small box, and also I got very good results. And now, right now in MIT University, Jaipur, I have the very good sensing unit. So if anyone wants to make the collaboration and then perform the experiment, they can come. They are most welcome. So till now, whatever on whatever material I have done work, so quantum, different kinds of quantum dots I have synthesized, and also the spinel ferrites, all kinds of spinel ferrites I have synthesized here. And then also using the quantum, different quantum dots, the core shell have been synthesized. And then using the core shell and the ferrite nanoparticles, I have synthesized the variety of nanocomposites. And all these materials have been tested for the different gases in which I utilize till now the LPG, ethanol, ammonia, chlorine, smoke, SO2, NO2, humidity, and acetone. So all those facilities are available in MIT University, Jaipur. If anyone wants to perform, then they are most welcome. So here, basically, I have the LCR meter and temperature controller, gas sensing unit, liquid nitrogen cryostat, vacuum pump, and 2D inkjet printing technology. So as we were discussing about the different properties of the cobalt ferrite nanoparticles, and all these nanoparticles of different size were tested for the LPG, and we have seen as the particle size decreases, the sensitivity is very high, and at the particular temperature, the sensitivity is giving the highest value. This particular temperature known as the intermediate temperature, over which the reaction of the test gas with the surface of the particular sensor and the diffusion of the gases becomes equal, and they give us the very high sensitivity at that temperature. So same thing were performed for the ethanol, and we got the better result, but for the LPG the result was excellent. And also for ammonia, all these nanoparticles were tested, but a little bit lower response we received. And then also the at different flow rate of the gas, we are able to find out the sensitivity, but at particular flow rate, the sensitivity becomes saturated. So basically here in this case, we can find out at up to which particular ppm our sensor is working. And the same thing we have just followed for the nickel zinc ferrite, and here it is very interesting result. Again, for ethanol, we are getting very good sensitivity. And as we are taking the x equal to 0, meaning zinc ferrite nanoparticles, and for nickel zinc ferrite nanoparticles, we are getting very good sensitivity for the ammonia. But that was not, we were not getting the sensitivity towards ammonia for the cobalt ferrite, very good sensitivity, but nickel zinc ferrite is giving very good sensitivity here. So meaning is that different ferrite nanoparticles are giving the different result for different response on the different gases. So basically here we are finding the two intermediate temperature. This is very interesting result, but in the cobalt ferrite nanoparticles, as you were seeing, and in the nickel ferrite nanoparticle, there were only the one intermediate temperature. But here in the case of nickel zinc ferrite, two intermediate temperatures are coming. So this basically because nickel is in the inverse spinel form, and the zinc in the normal spinel form, and both spinel structures are giving their own response. Therefore, we are finding the two intermediate temperature here also. So structure of the ferrite gives the very interesting feature always in application also. And here the zinc ferrite, because it is the normal spinel structure, so octahedral and tetrahedral both sides are involving in the response of towards the gases. And here we are finding the good sensitivity towards the particular gas. And with the help of the ferrite nanoparticles, I have synthesized the nanoparticles, nanocomposites, as we have discussed. Large number of nanocomposites were synthesized. Here I am taking the one. So here I have taken the barium titanate, carbon nanotube, and cobalt ferrite nanoparticles. And with the help of all three, I have synthesized the nanocomposite with the help of Sol gel synthesis. And this is the XRD for confirmation. All peaks are coming for BTO, CNT, and cobalt ferrite, and which confirms the formation of the nanocomposite. And here also we have the transmission electron microscopy images, in which CNT and cobalt ferrite with the barium titanate are clearly visible with the particular fringes, more fringes, and then also the particular planes. And quickly we are coming on the response as we have tested the particular nanocomposite for the ethanol, acetone, and NO2. And we are finding here as the flow rate increases, the particular sensitivity increases, and it is giving us the acetone. It is giving us a very good response for the acetone, but it is not too much response. But as the flow rate at the highest flow rate, the response of the NO2 increases. So here we can just find out the selectivity. As selectivity, everyone is not following in the research paper also, but here I have done the selectivity as ethanol has very less response, but the acetone and NO2 has very good response at the highest ppm. Then we can just make selective here our sensor between the ethanol and acetone. So I have taken this particular result in the selectivity, and I just also I performed the temperature varying the response, in which also I am finding the 2 and 3 intermediate temperature. And 2 intermediate temperature, again the particular spinel structure is working, and also the barium titanate and CNT including the is also including in the response. So here also, as I just given the information of the selectivity, so we can take selectivity at 30% and also selectivity at the 50% between the ethanol and acetone. We are just escaping here the NO2. So as we are filling the chamber with the 220 ppm ethanol, and then just injecting the acetone with varying the ppm, we are finding without combination, simply ethanol is giving you very less response, acetone is giving you better response but at higher ppm. So as we are just filling this at different ppm, both gases, then we are getting here the very different response. This is giving us the information of the selectivity, how our material is selective for in the mixture of gases. And same thing I have performed at the 50 degrees centigrade, and then I received the totally different response, as you are able to see in both curves at 30 degree and at 50 degree. So with the help of these kinds of experiment, we can just give the particular analysis over the particular material as a sensor. And then also I calculated here the activation energy and IV characteristic. And here in the particular graph of the activation energy, you are able to see the ethanol has a very good activation energy, as it is also giving us the better current and better current with the particular temperature. And also the activation energy at the different temperature range, you are able to see here the ethanol initially giving us the very good activation energy, as we are also seeing ethanol giving very good response. And also in normal atmosphere, our material in this case, the material is giving the better activation energy in the particular range, and in the same range the acetone and NO2 is also giving the better activation energy. Here with the help of this particular table, we also able to find out the selectivity in the particular sensor. And this particular concept of the combination of the barium titanate, cobalt ferrite, CNT came in mind as I wanted to just make the material more conductive for the particular electron as the during it is gaining during the exposure of gas. So as without exposing gas, the material absorb the oxygen, and as the gas injected, the desorption process happens and then one electron trigger. So we need to just need to just travel that particular electron. So therefore I introduced the CNT and then found the very good response due to this particular passage. So electron is able to travel and reach at the another side, and it is giving us the very good response. So with the help of these results, I just filed 2 patents on the same material, and then also on some different nanocomposites. I filed some more patents, so total 6 patents I filed, and then also I have completed 2 research projects from SERB and UGC DACSR. 1 project is in 3 more projects are in running state from ISRO Ahmedabad, and 2 projects from Hayal University, Saudi Arabia, in collaboration with the particular university. And quickly, I will just I will just show you the summary. So cobalt ferrite, nickel zinc ferrite nanoparticles were synthesized successfully and also found different kinds of properties, and utilized those properties in the application of the gas sensor, and also towards the gases LPG, ethanol, ammonia, chlorine, acetone, and NO2 gases till now. So some more work is in continue form, and some publications because whatever results I have taken from those publications. And before completing it, I would like to acknowledge the entire team and Honorable Chancellor Sir, Vice Chancellor Sir, Pro Vice Chancellor Sir, and the organizing team of this conference. And also I would like to acknowledge my supervisors and the collaborators from different institutes, and my PhD scholars. Those are working very efficiently, and my funding agencies and collaborators. Now you can ask the question. Thank you.
Thank you, Dr. Deepshika, for your wonderful talk on nanoferrites and their applications. So the session is open for the questions. No question. Okay. Okay. So as there are no questions, so now I request Professor Preeti Thakur ma'am to please present a memento to Dr. Deepshika Rathore. Thank you, ma'am. So now we move forward to the next, our next speaker, and this is going to be the online mode. So our next speaker is Professor Sabi Bakar. He has earned his PhD degree in electronics from University of Bordeaux in 2012. He has more than 15 years of experience in academia and industry in Tunisian and French companies and universities. He worked on the modeling of high temperature analog and mixed signal circuits. He is currently Associate Professor in Electronics in SEGELEC and member of IRCEM Lab, a joint laboratory with University of Rouen, Normandy, France. His current research works focus on backscatter communication, piezoelectric energy harvesting, RFID system, and emergent antenna technology for Internet of Things. So now I request Professor Bucker to deliver his talk. Professor Bucker, can you hear us?
Hello. Hello. Since Professor Savi is not here, so I would like to request Pravindra sir to deliver his lecture. He is outstanding scientist in DRDO, very old friend of ours, and is a good human being. I don't want to say so many things because you can find everything about him on the internet, and you will understand from his lecture, the persona. He's a very good orator, very good administrator, very good researcher. So I know him since last, I think, more than 15 years. So, sir, please.
Good afternoon to you all. Professor Atul Thakur, Professor Nagarajan, Dr. Prasanna, and all present over here. A very warm good afternoon to you. And at the outset, I thank ISRS and MT University for giving me an opportunity. Okay, thank you. Giving me an opportunity to talk to this esteemed audience in which researchers from various fields and faculty from various fields is present. I have gone through the proceedings of MAM 2023. It was really a very vast area in which presentations have been made, and mostly it was in different disciplines. So
I will not be able to do justice that I can talk like experts in the various fields like nano sciences or medicine or something like that, because throughout my life, I have worked in DRDO, and DRDO, as you know, is connected with defense technologies. And I have been in armament technology for almost more than 38 years. And in various military aspects for 4 decades, almost 4 decades. So my talk will be basically focused on how DRDO is contributing to nation's development and how we are strengthening the nation in terms of military might, and how we can enable the academia and the industry to do their contribution to help, in national building. So as you know that in India, DRDO is one of the major technology leader in various disciplines which are related to defense as well as to civil to some extent also. And recently, the government has mandated DRDO to enable academia as well as industry to, liaise and convert technologies which are available with the industry or the academia, the knowledge which is available with the academia to get converted into some military usage. What is that? Down. Yeah, I'll start with our leader, that is Prime Minister Modi. And he is one of the, the biggest driving force behind us and where we have reached. As you know that he has very well guided DRDO to realize technologies indigenously and deliver systems indigenously. Our long-term goals, global competitiveness will depend not only on replicating what others have done, but will emerge through a process of sustained development and innovation. Basically, what he wants that all the technologies, earlier in defense, we were importing technologies, but today we want indigenous solutions for Indian needs. So I have divided my talk into 4 or 5 areas. One is that national security perspective. What is our national security aims? Security as a big business opportunity. Then bit about DRDO. And you must have been hearing from DRDO scientists from day one, because during the inauguration itself, chief guest was from DRDO, and then there were many speakers from DRDO who must have spoken to you on various technological aspects on the areas in which they have been working. Then the key initiatives of DRDO, and then finally we will discuss that how we can help the researchers in the university to realize their dreams. So as every one of us know, that national security basically means protection of almost all our cherished things, our democratic way of life, our institutions of governance, and our unity, welfare, and well-being of each and every one of Indian citizen. That basically means the national security. And it is the duty of the government and the government agencies to realize this national security in a way that every citizen of this country is feeling safe and sound in this particular area. Now, what are the various threats to our national security? There are, as all of us know, there are 2 different types of threats which are there. One is that internal threat. Most of this comes from various kinds of, troubles which are like terrorist attacks or Maoism or many other things. So many things are there as internal security threat. And external threats are from our neighbors, which you are very well aware of. So I will not discuss much on that. But as far as we know that national security comprises of many things. Some of them are listed over here, but I will mainly focus on multi-standing, then technology might, and industrial base. So these are the three areas in which DRDO is making a big contribution. Though there are other things also, for that there are other agencies which are working on it, but these are the three main areas in which DRDO have been working and mandated to realize our security. As a matter of fact, each and every one of us is a key stakeholder in the national security. But as far as the government structure is concerned, there is National Security Council, and this National Security Council is having three elements. One is National Security Advisory Board, then strategic group, strategic policy group, which basically, develops the strategy for the national security, then Joint Intelligence Committee, and various kinds of ministries are there for this particular thing to realize. And then you have services, which basically consists of Indian Army, Indian Air Force, Indian Navy, and then the fourth wing is DRDO. DRDO is helping all the three services to equip them with the basically equipments and systems which can help them in maintaining the national security. Now, if you see over the last 1 decade, that is 8-9 years, there has been a paradigm shift in our policy. And this paradigm shift is visible and every Indian citizen is realizing it. Earlier on national security, our approach was regional. We were basically, looking at only our neighbors. But now the shift has been there. It has been from regional to global. Then earlier, we were happy with defending ourselves. That is just defensive. If somebody attacks us, we defend ourselves, and that is good enough. But there has been a change in this policy also, from defensive to responsive. If somebody attacks, we retaliate, and we retaliate with full might. That is another important thing. So that the offensive by others is prevented in the beginning itself. That is called nip the evil in the bud itself. So that others will not dare again that we should do some harm to this country. Then another major shift that has happened over the last 7-8 years is from imports to exports. It is the strategy and the policy of the government now, right now, that we have to minimize our imports of defense equipment. That is the mandate. And that's why in the further few slides, I'll show you that how this defense or security is a big business. This slowly we have started exporting defense equipment. I'll show you in my future slides, further slides, that how the Indian government is helping the industry, Indian industry, to realize the things, manufacture the things under Make in India program and then export it. Then increased dependence on indigenous system. This is another message, that there is no need to import things which we can manufacture, we can create within India. So national security is now giving a big business opportunity for Indian industry. And at the same time, it is giving a big opportunity to the academia also. Why I'm saying so? Because, Indian industry is new to this business. They are new to manufacture all these things. So basically they need support, academic support, technology support, research support from academia. And that has to come from academia only. You see, this is how the projected annual spending of national was done on national security in 22-23, the year that has just passed. If you see, approximately 5,69,000 crores were spent on the security alone, which is basically approximately 50% of the India's total budget. So it's a very huge amount. Generally, countries, they spend less than 10% on their security. But India has been a country which has been making huge expenditure on its security and on its basically maintaining the forces. We have one of the largest army in the world, one of the largest, and very, very competent army in the world. And over 1,52,000 crores were spent on buying equipments and other things. And that 68% of this capital procurement, which was earmarked for the domestic industry, it was up from 58% to 68%. So we have enhanced the budget and Indian industry has got an opportunity. More than 1 lakh crore is available for, to supply equipments to our Indian army. So what impact it has? It has impact world over. It has an impact world over. A very strong signal to foreign manufacturers and suppliers was sent with India's resolve to indigenization. What has happened? Now, most of the arms manufacturers of the world, they are forced to have their factories and industry within Indian space, Indian area. So lot many industries are coming up, and you must have heard or you must have read in papers or media that lot of, defense corridors have been created. Like one near Lucknow, another in Bangalore, another in Chennai. So defense areas are, defense corridors have been created. This will not only give the employment opportunity to the youth, the young engineers and scientists, but at the same time, it will give and save a lot of foreign exchange, which was earlier flowing out. So this is one of the major impact of this particular decision. There has been a paradigm shift in, philosophy of war. Earlier, there was a philosophy that we used to have a direct conflict, but now it's not so. It's basically changing to proxy wars. And it's very difficult to handle proxy wars as compared to, direct conflict. Indian army is strong enough. I'll say that no neighbor will ever dare to have a direct conflict. So direct conflicts have been ruled out, but at the same time, indirect conflicts and then proxy wars, asymmetric warfare, it's on the rise. So all researchers and all scientists, they have to think in different way. Now, you must have heard of that there are drones intruding from across the border. They are dropping something inside. They are dropping equipments, explosives, and this. So that kind of a situation, for that you need different kinds of equipments. Like aircrafts, you can very easily detect by using radars. We have got a very strong radar base for as far as intrusion using aircrafts are there, because their signatures are quite high. But drones, it's very difficult. So this is one of the areas in which you can work, or the researchers can work, that how to detect these small flying objects, how to detect that. That is one of the challenging areas. So I'll tell you about bit about DRDO, what DRDO is doing. In India, you have three main research organizations. One is ISRO, and ISRO is mandated to, launch satellites and have rockets and all that. So they have got only one domain, that is their space. Then we have another very important organization, which is DAE, Department of Atomic Energy. They also have one focused area of research, which is basically their atomic energy. In that area they work. Then there are CSIR laboratories also working in different areas, but three main giants which get the R&D budget, maximum R&D budgets are DRDO, ISRO, and DAE. These are the three main organizations. DRDO is one organization which is working in a very vast area, almost all the disciplines. You think of something, it will be there in which a particular DRDO lab is working. So DRDO is basically having a huge spectrum of R&D and systems development. Just to remind or just to give you a quote by our ex-president, who was the chief of DRDO also, President Dr. APJ Abdul Kalam. He used to tell, it is strength, strength respects strength. So if you are strong, others will salute you. If you are not strong, they will kick you. So this is one thing very important. So it is the primary duty of all academia, industry, and the scientific research institutions to make us ourselves strong enough in terms of technology as well as military might, which we have told you earlier. So this is basically the job of DRDO, to give you technologies and systems so that we become one of the strongest nations in the world. And how we are doing this, or what approach we have a trident approach, which basically says reduce imports in defense to the extent possible. Then enhance combat effectiveness. I'll come that what all we need to enhance this combat effectiveness. Then create strong technology base. It's not just that if I have a rifle with me, I am strong. I have to have many other things in addition to that, so that we have not only military, we become a military power, but at the same time an economic power also. And we can become economic power only if we have a very, very strong technology as well as industrial base. So DRDO is mandated to do this job also. So DRDO, we have, we have, different clusters based on our technological needs. We have divided ourselves into clusters. We call them technology clusters. So first and foremost is the aeronautical systems, or the aero cluster. Then it is armament and combat engineering, which basically deals with the armament systems, then electronics and communication systems, then life sciences also. Life sciences is very, very important for DRDO, because ultimately, who is a soldier? Soldier is a human being. So all the things move around him. He is the center of each and every development. So we will discuss that how we can help a soldier. Microelectronic devices, electronics is there in defense in a big way. Everything is nowadays smart, and everything is revolving around electronics. Then you are very well aware, missiles and strategic systems. Missiles is also one of the strengths of DRDO, and one of the power in the world that who has got intercontinental missiles. You must have heard of Agni 5, then BrahMos, then so many other things. You must have heard of it. The naval systems and materials. If we want to have a global reach and global presence, Navy is very, very strong. Navy is a must. If you don't have a strong Navy, you cannot become a global power, because Army will remain around your borders. Air Force can have a limited reach, but it is Navy which takes you around the globe. So Navy is one of the important thrust areas, or naval research, naval systems, one of the thrust areas. And you must have heard of in the recent news or recent media reports, we are having some exercise. Navy is having some exercises in our Eastern Sea, near to China. So as I told you, canvas of DRDO range of activity, it is very big. You can think of from starting from a small grenade to a big bomb, that is nuclear bombs, then starting from small rockets to Agni 5 missiles, which have got a 5,000 kilometer range and capable of carrying strategic weapons, that is nuclear capable, or we call it nuclear tipped missiles. Then from parachutes to Tejas aircraft, which is one of the best aircrafts as of now, combat aircraft, light combat aircraft in its class. Then from rifles to artillery guns. So all these areas we are working, and anybody who has got an idea in a particular research area, they can contribute, because these systems are very complex systems and require a lot of materials, require a lot of different types of materials. So you can contribute in that particular area. Then it's not only just weapons, food also. Can you contribute in, having high energy food for our soldiers who are staying in minus high altitude like Siachen, like Kargil and all that? There the food requirements are entirely different. They need, very high calorie rich food. At the same time, we have to reduce weight also. Then torpedoes, as I said, then nuclear powered submarines. We have worked in a particular area, and now India is having nuclear powered submarines. You can, Arihant, you must have heard of the name Arihant, which is there. And in this class, there are many. As I told you, if we have to become a global power, we have to have a strong navy. Then materials, clothing materials, that is also very, very important. Clothes. One of the important turning point in Indian history was 11th May 1998. Now almost on 11th May, another week, after another week, we are going to complete 25 years of that particular event, which made India a nuclear power. So it was possible because of the efforts of DRDO and DAE scientists, and India became a nuclear power. As I said, Arihant is a nuclear capable, nuclear powered ballistic missile submarine. So to have a global reach, we have this particular weapons, this vehicle, which is really one of the best in the world. More details you can get on internet also. That's not a issue, big thing. But the important thing is that its range, it can take you around the globe. It can, without, refueling, because it's nuclear power. Main battle tank Arjun. This is also one of the best tanks which is available, and it's a match for, Abraham 4 or other tanks of Russia, T-72, T-90. It's a match to that. It's a state-of-the-art tank with high mobility and excellent protection. So this is one of the things which is a feather in the cap of DRDO. Missiles, again, these are the important things. Missiles and missile technology, we are the leader in the world. And thanks to academia, many institutes, IITs, universities, they have contributed in realizing these particular missiles. Most of the technologies, they have come from, academic research, because generally you won't get technologies from, from outside. So you have to indigenously develop all these things. BrahMos is one of the best cruise missiles which is available, and India is exporting it to friendly countries. This is the complete range of ballistic missiles, more than 15, 16 different types of, for different applications. So it will start from Prithvi to Agni 5. Tejas. How many of you have heard of Tejas or LCA? Yes. This particular aircraft is totally an indigenous effort, and now Indian Air Force is going to be equipped with this particular fighter aircraft, and India is going to export it also. So one of the great success and one of the best aircrafts, fighter aircraft, light combat. DRDO has not only contributed, to enhance the military might, but we have done a lot during, COVID also. During COVID call, DRDO has constructed around 7 COVID hospitals. In Delhi, 1,000-bed hospital, we constructed in just, around maybe 45 to 50 days. That was one of the, biggest project which was executed in such a small time. More than 100 crore project just executed in 45 days. So during that period, in a small time, we not only developed the 2-deoxy D-glucose oral powder to combat COVID, but we designed and developed 2 important things. One was the ventilators, which were subsequently manufactured by Bell in a large number. Earlier, we used to get these ventilators at a price of around 25 to 30 lakh per ventilator from import. Now the cost has come down to 4 to 5 lakhs. And those ventilators are supplied throughout the country in large numbers. And it was manufactured in a record time by DRDO and Bell Bangalore. So you can go to the site, website of Bell Bangalore, and you can see that how and that particular system was developed in a very small time. Similarly, the oxygen was in big demand, but the oxygen equipments were not available. So DRDO developed these oxygen concentrators. They converted the technology which was being used for LC. So, in a fighter aircraft, there is no pressurization. They carry oxygen concentrator and they have that oxygen small equipment which generates oxygen. So that particular thing, technology was scaled up so that it can be used as a medical oxygen. Okay, so in various hospitals, government hospitals, if you will go and see the oxygen plant, you will find that a DRDO logo is there on that. And in many of the hospitals, it was, under my supervision, it was, installed. Now, coming to the real issue. See, as I told during my initial slides, that everything moves around a soldier. See, infantry soldier is the most important person in any defense system. And that particular, all others, whether it is Air Force, whether it is artillery or other people, they are all there to help him fight the war. But the infantry person is the most important person. And as far as we are concerned, I can say he is the most neglected person also. What happens is that he is the person who has got minimum attention. Okay. But now we have a very, very huge program, big program to make the soldier a very comfortable and a very fighting fit soldier as a system. So this is very important. We want to equip him with the latest technology, as well as we want to give him the maximum protection, because he is the person who is, facing the bullet. He is the only person who is facing the bullet of the enemy on the chest. So these are the various things which basically can go into this. You can work on head-up displays. Head-up displays are something, say, in addition to the helmet, which protects his head or gear from the bullet, it can add, you can add many systems which can give him the night vision capability, which can give him many other communication capabilities. In the battlefield noise, there is a lot of noise. So it's very difficult to communicate also. So you can design and develop communication systems. Then bulletproof jackets. See, what we feel today is that if you put a bulletproof jacket, you are safe. It's not so, because different kinds of bullets, different energy of bullets, they can defeat. So you have to give a bulletproof jacket which can, stop, different kinds of bullets. Right now, we are importing these jackets from various foreign sources. Materials are being imported from various sources. Our researchers should work to create those materials. And I think one of my colleague here, Dr. Sanjeev Verma, he must have spoken about, yes, he must have spoken on this particular topic. So this is one of the, biggest research area today. Ballistic protection, ballistic protective materials. One thing, we are totally dependent on foreign source, that is Kevlar and Dynama, but can we have some alternative to those things? Because the cost which we are incurring on buying bulletproof jackets is huge. It's huge. Then helmets again, they add to weight. That also we have to see. The night vision, assault rifle, armor, shoes, communication, everything, See, as I said, infantry soldier is one of the most loaded person. You can see he carries basic three things. War fighting equipments. He has got a lot of war, rifle hai uske paas, ammunition, then light thermal sight hai, grenades hai, knife hai, and many other equipments he carry, like even a rope he carries. Survivability gadgets, in which combat helmet is there, body armor is there, communication, GPS, power pack, then sustenance kit. If a soldier goes on a mission, he carries water, he carries food, he carries, 3-day ration, then uniform, everything he has to carry. And if you add up all this weight, it works out to be 30 to 40 kgs. And the average weight of an Indian soldier? 60 kgs. So he is carrying 60% or 50% of his weight. And you can just feel that you carry some 5 kg bag for some time, and then just realize that how much punishment, how much physical torture he is going through. His rifle alone is 4.5 kgs. And he is carrying bullets. Some 210 odd number of bullets are given to him. A cartridge of 30 bullets, 7 cartridges, he puts it here. So that also weighs, 4 kgs. So 8 kgs of ammunition weight. It's heavy load. And then if you put on him a protective, jacket of 8 kgs, 10 kgs. So it's very difficult for him to, climb those altitudes. Another thing is, which is very, very, important to work upon. They are, our Indian soldiers, they are fighting in a variety of terrains. And terrains are from Rajasthan to Kashmir and Northeast, all these areas, where in some areas you have got a lot of heat, like Rajasthan. And in some areas you have got temperatures which are -20, -30, -40. And in some area, a lot of humidity. So all these varied things, but he has got a single uniform which has to suffice in all these 3 areas. So we have to work upon such systems that he can sustain in all these different terrains equally efficiently. So this is very important. So what basically the heavy weight and bulk of body armor decreases soldiers' performance. अगर आपको भी लाद दिया जाएगा, if you are also loaded, you will not be able to function well. So same is the problem with the with the soldier, not only Indian soldier, world over. So same problem. Then heavy loads affect mobility, then situational awareness, and leading to measurable decrease in shooting response time. See, if you are heavily loaded, your agility has been reduced. So it will be very difficult for you to aim and fire and kill. And in the meantime, you can get killed. That is one of the things. So soldiers face trade-offs between mobility, protection, and lethality. So at times, what soldiers do, this has been a practical problem. What they do is, वो जो bulletproof jacket उनको दी है ना, वो उतार के side में रख दे. And they fight without that. And as a result, sometimes they get killed. So what is the solution? Or what solution we can offer? Can we offer a lightweight ballistic protective system? So that is one of the most important things. Then heavier loads also increase fatigue. If you are loaded, fatigue, so they get tired. So can reduce overall mission performance. Technology, sometimes we add more and more things. हमने उसको communication set दे दिया, हमने उसको helmet में एक night vision device दे दिया. So many things we have done. But what is happening because of that? They add more load to the soldier, more load. So sometimes, technology, soldiers don't like. They don't want, binocular. वो कहते हैं यार 2 किलो मैं एक्स्ट्रा लेके जाऊंगा, why should I carry it? So what is the solution? See, solution is reduce weight or cut weight by using technology and by using sophisticated materials. But what happens sometimes, these sophisticated materials, they become expensive. So same thing, if I have got something which is costing me only 5,000 rupees and I get a better thing which is 10,000 rupees, sometimes our decision makers, they don't like, or they don't agree to that, because that is adding to the cost, and ultimately that cost comes on us, that is a taxpayer. I'll give you one small study or case study. One particular item the soldier carries, earlier design, it was having, which we call it the M36 grenade. Grenade is one of the important equipment which infantry soldier carries. You must have heard of it and must have seen it. That used to weigh 740 grams, 740 grams, because that was made of materials which are steel and all that. So it was heavy. And one soldier is issued 2 grenades. And it is essential because that is one of the area weapon he has. Our laboratory, TBRL, we designed one plastic grenade. Now this particular grenade, which is now in the service and army is having it, it weighs only 500 grams. So basically the weight reduction of overall 500 grams. So similarly, if we work on each and every item which a soldier carry and reduce the weight, so it may happen that instead of 30 kg, the overall weight which the soldier is bound to carry is going to reduce to 20 kg. So it is going to help the soldier. So that is important in each and everything. I do not know in what areas you are working, in what materials you are working, but you can identify one particular material, maybe textile, the thing he is wearing. That is also very important. हम कपड़े पहनते हैं, we wear this and we go out, and if we get wet, then we come and change at home, we dry up. But when a soldier is in a battlefield, if he is wet, what will he do? What will he do? So one of the requirement is, and world over research is going on it. Can we have a textile which prevents water going from outside to inside? But at the same time, it allows the evaporation of the sweat from inside to outside. So some material, some textile material, which is allowing only one way, passage of the water, that kind of a thing. So this is one of the areas in which people can work, and it's a big requirement. And if somebody is able to, get a breakthrough, he will be a multi-millionaire. So this grenade, it was accepted by the Indian Army, and now, approximately per year, 600 crores are being saved from foreign exchange as far as this product is concerned. You can just have an idea. One grenade is costing about 6,000 rupees, and about 10 lakh grenades are required per year. So it's approximately 600 crores. But at the same time, its export potential is also very high. And there are, many buyers, because such a cheap, grenade you won't get from Western countries. If you have to get this kind of a grenade from Western countries, it will cost you about 10,000 to 12,000. That kind of saving you have. And it is a very big hit. It was, Raksha Mantri, then, Chief of General Staff, and then DRDO chief, they all were there in a big function when it was inducted into the service. More details you can get from internet. That's available over there. Then there are, as I said, for Navy also, another important thing on which my lab and I have worked was torpedo, which is called Varnastra. This is a weapon system which is anti-submarine. If you have a ship or a submarine, if you want to destroy it, you need to have this. This also has got export potential. And it's worth 17,000 crores of orders we are going to get. And it's being manufactured by Bharat Dynamics Limited at Hyderabad. So that is the kind of this thing. And Indian industry, private industry is also participating in its manufacture. They are bidding. They are, bidding for various types of systems. So not only these two, there are many other, more than 700 items are there for which you can pitch in. But I have just given you the two examples. Now, the biggest, the problem with Indian setup was that there was no, linkages between academia, research institutes, and industry. What is happening is academic institutions, they are working in their domains. And what is happening, they are happy with the, publishing some research papers in some good journals, earning PhD, and then putting that knowledge into shelves. So that knowledge is not getting converted into, effective technologies. Or even if some technologies are there, they are not seeing the day of light in the form of a business package. It's not coming up. It's high time that our industries, our institutions, our universities, they start a setup within their boundaries and help, what you call incubators for startups. That is very important. Small technologies which you develop, they should get converted into a product. And money comes from the product only. No knowledge. ज्यादा एक पेपर में से आपको कुछ ऑनरेरियम आ जाएगा, उससे ज्यादा कुछ नहीं आता. But it is basically the product which brings you the money. So DRDO is helping in, doing the startups, in taking the CARS projects, in various research projects. And, we do funding also. Funding. There are systems, I will tell you how you can go through that and then get the funding from DRDO. Government has released one list, which is, I think all youngsters should look at. That is called Make One for defense items. See, there is a list, make one and make two. In that particular list, many items are listed. If some entrepreneur wants to, work on that and produce those items for Indian Army, so that items are listed and government is going to fund you for setting up the setup. So that is available. See, in DRDO for this particular thing, we have set up a technology management cluster. So there is a dedicated group at DRDO headquarter level, which is being, headed by what you call Director General Technology Management, a officer who is of the rank of, you can say, level 15, that is above Joint Secretary, Additional Secretary rank officer. And under him, there are 3 directorates: Directorate of Extramural Research, we call it DER and IPR, then Directorate of Futuristic Technologies Management, DFTM, then Directorate of Technology Development Fund. So these are the basically the directorates which are there to help you, in this particular area, in your projects. Then we have got research boards. Research boards are Aeronautical Research and Development Board, Armament Research Board, Life Sciences Board, and Naval Board. And I'm happy to tell you that some of the institutions, they have got projects worth 5 crores and even more. The project proposal should be sound enough and it should be realizable. Then you can get the funding, no issue. And I am a member of one of the boards. So if somebody wants more information, they can approach me. Dr. Thakur has got my details, so you can always approach me. See, the most important means with which we interact with academia is contract for acquisition of research services. DRDO laboratory development projects, then knowledge gap we identify, then academia, the people who are interested, they should take up and send a project proposal. One of the participant was asking me that, how we can do it. See, how do you do your PhD? How do you select a topic for your PhD? See, very simple thing you do is, first you have got the desire to do PhD. That is the basic thing. And then what you do is you identify a topic. And then for that particular topic, you try to find out who is the person who can guide you. So in the same fashion here also, you have to have the desire to do a CARS project first. And then you have to identify a topic. And there are so many topics listed on the DRDO website. If something matches with your interest, you pick that up. Otherwise, if you have some interest in which you want to do that particular research work, then you have to see whether it merges or it merges with some DRDO requirement. Then you have to identify a laboratory and a scientist. If you are able to find out a scientist, your problem is solved. Then he will, put up the things for you. He will work for you. But the thing is, only important thing is that the work which the area in which you want to work should be of DRDO's interest. That is important. Otherwise, funding will not be possible. But in this particular, if the work is important and it is a requirement of DRDO, you can get funds up to 5 crores. No problem on this. Okay. So this is one of the most popular method, and we have got many projects with IITs. Even Dr. Atul Thakur also had done one project, those
Yes,
small,
yes, sir.
through this means.
Yes, that time maximum limit was 10 lakh. Now I suppose 25 lakh.
It's
Ca-
5 crores.
5 crores. Okay, for cars.
For cars.
Okay.
So see, the government has opened up. It's not because of the DRDO, it's because of the government. Government has opened up and government has asked DRDO to spend 25% of its overall allocated budget through industry and academia. So that is another important thing. We are perforce, forced to spend through industry. Okay. That was one of the major announcement of our finance minister, Mrs. Sitaraman, during 22 budget. You must have heard of it. 25% जो है DRDO budget का through industry spent on. So that was one of the major, change in the strategy, because earlier DRDO was working within itself. But now when we are forced to, allocate funds to industry, so definitely we will give projects. Otherwise, there is no other means way. See, then another important fund that has been created, and it is also having a kitty of 500 crores. That is also very important. Technology Development Fund, TDF scheme. If you have some idea and you want to develop a technology that can promote self-reliance in defense technology, then you can approach DRDO. No doubt about it. The aim is, eligibility is any individual, any public-private industry, anybody. Or you can make a group also of 3 people or 4 people, and then come up with a proposal. Like right now, many people have come up with the proposals to, develop drones. Drones is one of the big things. So many industries have got, projects to develop drones. Many industries have got projects to, develop batteries. Okay, battery or power source is also a big challenge today.
Yes, sir. We also submitted one, sir, through a startup. It was for radar absorbing material, and the parent lab was Defense Lab Jodhpur. We made the presentation. Now we are waiting for the results. The total budget was 5 crore. No, through startup.
Research board.
Through not board, through lab.
Okay.
Yes, sir.
Give me reference.
Definitely. Sir.
Okay. So in this, TDF, already some 1,630 industries, then 514 individual experts, then academia institutions, basically 299 institutions. Earlier, there was a inhibition to give, projects and these things to private universities. It was some mindset, I'll say that. But that mindset has, changed now. It's not that private universities are seen inferior to the government universities. So you can take up anywhere. We have got, center of excellence is opened at many places. Center of DRDO funded. Even in IIT Delhi.
Yes, mostly at IITs, sir. Huh? Mostly at IITs.
No, earlier it was, I said, no, earlier there was a mindset about the government. Now even private universities are pitching in, and private universities are also getting centers from DRDO. Only thing is that private people, they have to do little more effort as compared to government. Yes, that's the only thing. So in this particular, there the limit was 5 crores. Here it is funding up to Rs 10 crores can be given. And very, you don't have to spend much. You don't have to spend much. It's all government funding. Then another thing, this is not a DRDO thing, but it is from ordnance factories. Okay. There are so many problems which basically you can, work upon. So IDX was launched by the Honorable PM during the Defense Expo India 2018. So basically, again, the same thing. Here also, you can work on problems which are related to manufacturing. Okay. See, we have got industry, ordnance factories. They get every, they manufacture so many things for our Indian Army. And during manufacturing, they face certain, research issues. So to, tackle that particular thing, this particular fund was created. And this corpus is 150 crores as of now. But again, it can be enhanced, and many industries, they have, jumped into this, like manufacturing of a gun barrel. Manufacturing of a gun barrel itself is a highly challenging task. And Bharat Forge, you must have heard of it. They have got a project on this. Similarly, like I said, rifle. Rifle is the most common equipment which a soldier carries. और उसमें सबसे भारी, the heaviest component is the barrel. If somebody can, design a better material rifle barrel with lightweight, the rifle weight from 4 kgs to 3 kgs, it will be a big challenge. It will be a big boost. That rifle will be hit world over. Okay, so finally, with this small, introduction to DRDO as well as to the various mechanisms through which we help industry and the academia, I would like to again give a quote from my favorite leader, that is APJ Abdul Kalam, because हिंदी में ही बता देंगे. See, I have been very lucky because I got opportunity to work with him. He was one of the scientists who, used to work with his own hands and with the people on the ground, on the lab. So he used to come to our lab, and it is his vision that we became India's, we became nuclear power and then missile power and all that. And we used to feel, elated when he used to come and see us and discuss us. And one of the great thing with him was he called each and everyone by name. मैं scientist B था. Scientist B means just a new entrant. But he came to our lab. We were working on a particular thing. He discussed the things with us. Then after 6 months, again, he came to review us. And to our surprise, yeah, scientist B ko kaun janta hai? But he was such a person who called people by name. And we were surprised. So this is the greatness of this. And he never used to, जिसे कहते हैं ना yes, he was like a very, very simple, ordinary man. He will come to lab in a chappal, jaise aa gaye, he will that way. So, but he was a learned man, he was a philosopher, mentor, and he was a great motivator. So, इंतजार करने वालों को सिर्फ उतना ही मिलता है जितना कोशिश करने वाले छोड़ देते हैं. So, basically, don't wait. He used to say, if you have got an idea, see, ultimately it is the value of the idea. जिसके पास idea है, he is the richest man on the earth. और जिसके पास idea नहीं है, he is the poorest person. So value is of idea, but that idea is of no use if you don't work for it. So don't wait and just start working. Maybe आपको 10 बार धक्के खाने पड़ेंगे. You know, woodpecker, what it does?
Keep on knocking.
Keep striking again and again. Ultimately, you will get something. And I personally have, seen the result of this particular, which is called, that try again and again till you succeed at last. I tell you, one of the projects which we say that Fuse project we have in TBRL. Fuse is one of the very important device of any weapon system. It took me 2.5 years to get that project. 2.5 years. People were not, convinced about our capability. So you have to demonstrate your capability. And that capability by, striking time and again. बार बार आप कहेंगे, बार बार आप, उसको pursue करेंगे, you will get the result. Otherwise, एक बार किया, 2 बार किया, थक गए, छोड़ दिया, you will not get the result. So take pride in how far you have come. Have faith in how far you can go. Okay. So this is very important. Believe in yourself and you will be able to do. So with this, if somebody has got some questions on any of the things in which area you can work for DRDO, you can ask. No issue. Yes, madam, you had many questions.
Yeah, thank you, sir, for this informative talk. Firstly, I am looking for a very good project, sir. So as you have given the ideas, definitely I have more ideas, but I would like to collaborate and.
Say, I saw your presentation and you are working on, gas detection.
Yes.
And this is one of the requirements also of one of the, projects. See,
Okay.
ultimately, when we discuss on NBC, nuclear, biological, and chemical warfare,
Yeah.
so basically, chemical detection is one of the important things. So I can suggest you, there is one lab which is working on this particular area, which
Okay.
is DRDE Gwalior.
Okay.
Go to website of DRDO. There you will find DRDE Gwalior.
Okay, sir.
You drop a mail to director DRDE. Okay.
Okay,
They will
thank-
definitely come back.
Yeah. Thank you, sir, for information.
So, but that is a very good thing because we are looking for these kinds of detections. Two detectors we are looking for. One is explosive detector. Okay.
Yeah.
At airports, if somebody smuggles in explosive or smuggles out something, so you need a detector. Right now, there is no method. What they do is sniffing through dogs, which is also not very, where is it? Okay.
Stop sharing.
Thank you, sir, for your wonderful talk. And DRDO is like lifeline of our country.
Maybe
We
we
are
can
honored.
take one or two more questions.
Yes, sir.
because
Yes, sir.
it's
Please.
Inspiring, interesting talk given by Dr. Kumar, and therefore there may be one or two more questions. I think would be a great idea.
Yeah. Good afternoon, Professor P.V. Sharma ji.
My great pleasure, sir. I was listening to your lecture. Please, yeah.
I am Dr. Prasanna Raj. Namaskar, Sharma ji. This great man has done, as a doctor, we do surgery. He has done a surgical strike here. He has opened the panorama box of innovation. And the whole program is, very, very educative. Earlier, there was a speaker from Chennai who was speaking about the drug delivery. How we can see that the medicines can reach the target organs in cancer or something. Very, very well organized and highly educative. And I never knew that our defense system is so creative and innovative and at the same time rich.
I think after this talk, we have understood the meaning of Atmanirbharta, which is being the main focus actually of development of our great nation and great work being done by DRDO, not only to ensure Atmanirbharta in the defense sector, but also to ensure its benefits also percolate to the civil as well as societal actually sectors. And the industry, of course, is one of the major players. And I was very happy that the call for industry, academia, and DRDO joint partnership and working together for achieving the great goals which we have in front of us has been given by Dr. Kumar. We are so happy to hear you, sir, and I'm sure you have set the tone that this is the century of the ideas. And because this is the century of the ideas, it requires ideas to be taken up with courage and confidence and with conviction in partnership with the industry as well as with the R&D organizations. And it is this troika of industry, R&D organization and academia working together, in fact, will create the win-win situation for a country like ours, where both the quality of education as well as research will go up like anything, at the same time contributing to self-reliance and taking innovation to new product development of the kind that we require. I was particularly impressed by what you said, that through nanoscience and technology, we are in a position to cut down the weight of very many systems and devices and products that we utilize in defense. Weight is, of course, very, very important. Alongside with weight, I'm pretty sure we are also cutting down the consumption of energy. And energy efficiency becomes another very important benefit coming from nanoscience and technology oriented research and development that leads to product. But the third and most important also is that we are also able to enhance the sustainability, and therefore the bare minimum damage to the atmosphere is something which we now have to keep in mind. And nanoscience has a great promise to graduate to that level. Already we are finding its multifunctional applications which will solve the problem of climate change, the pollution, capturing carbon dioxide, and also at the same time giving us hope that net zero emission systems are possible. So we are keeping, in fact, in our university, a very, very tight program on nanoscience and technology, ensuring that its multifunctionality and multi-application orientation is pursued by our scientists within the university. Dr. Thakur, Atul Thakur, Dr. Preeti Thakur, Dr. Krishnaiya, and several other scientists who are working in this group, they are very much conscious of the spread and application of nanoscience and technology. And I was very happy that they are also working with DRDO. People like me also have experience of working with DRDO, especially Aeronautics Research and Development Board, with whom I had several projects at IIT Delhi. And I personally feel that there is a great advantage in working with DRDO. Not only we serve the country and contribute to self-reliance, we also have tremendous amount of learning to come by our partnership with the defense scientists. In our own university here, in collaboration with DRDO, we have started Master's MTech program, Master of Technology program in Defense Technology last year. And we found that the quality of students which we got, they are so inspired, and each one of them got their internship in the DRDO research laboratory, and they all are placed so well actually. And programs like these, along with, of course, multifunctional partnership between defense and industry and academia, would do wonders. People like me are here to also create the Panchamrit, which means we need to keep in mind what industry, academia, R&D organization can do together. But all this need to be aligned to the national objectives as set out by the government policies and programs. Atmanirbharta is one of them. Swachh Bharat is another one. Make in India is another one. Digital India is yet another one. Hydrogen economy is yet another one. Circular economy is yet another one. All these missions, in my opinion, also could be very well supported by working together with the industry and R&D organization. And I want to take government also on board in all our activities, and also the society, so that all the 5 components which together create healthy and happy society and a developed nation could be served, in fact, through our partnership of working together. So I really want to express my profound gratitude to you, Kumar Sahab, for sparing your highly valuable time and giving us window of the kind of exciting work that is going on. Dr. Prasanna Kumar, sitting in the front row, has certainly mentioned that this is eye-opener for each one of us, because many of the things in defense earlier were not known. I never understood how important the design and development of the grenade could be. Being a peace-loving person, I was thinking I will not throw grenade on anyone. But surely Atmanirbharta and having capability to defend ourselves from our enemy is also very, very important. So we will all are quite excited here in our Amity University, Haryana, and I'm sure so are the founding fathers of Amity University, including our honorable founder, president, and honorable chancellor, who would be very happy to know that an address like yours, such an expert talk has been delivered in this conference. So we are grateful to you. Ladies and gentlemen, I would be logging off shortly. Just wish to say that this conference has been a great value, had a great value not only to us, but also to great many researchers who are participating in this 3-day conference to give us, in fact, the window of things to come in the arena of nanoscience and technology, research and development. They will cover the applications for defense Atmanirbharta. They will cover, in fact, the capability that we require for mopping out enormous amount of water pollution, air pollution, as well as to achieve our lofty goal of net zero emissions by 2035. They will also give us capabilities of revitalizing and revolutionizing our capabilities in manufacturing in India. And India would then be able to provide the leadership of the kind that we require. And therefore, at this closing hour of the conference, which you will have in the valedictory function, keep the objective of Atmanirbharta as number 1, transformative technology and mind-boggling and path-breaking science development as another one. And the third one, ensuring that India leads in the areas in which it has such tremendous strength. We are a country of young people who are highly inspired, deeply dedicated, they are innovative, they are highly creative, and many of them are now showing that they are also highly enterprising. So this enterprising and innovative and inspired minds of young India, I'm sure, is a great promise for creating India of our dream. And I, as a Vice Chancellor of the university, would do everything possible to ensure that my own faculty members and research scholars and students here get excited and get connected to DRDO for the larger objective of creating that vital self-reliance for our country and leading India in sector which is so important. I thank you very much indeed, and thank all the participants for coming together for such a great conference. Thank you, Dr. Prasanna Kumar, because health sector is also a very important sector, and nanoscience and technology has a great promise for you, including the oxygen concentrators, which Dr. Kumar has shown, and also, of course, the ventilator. But beyond that, we also want to partner our efforts in nanomedicines and also in nanomaterials, nanoparticle coated materials, which will solve the problem of tomorrow. We want to develop, in fact, textiles of the kind which will make our doctors fully safe under the most hazardous environment of the kind. It would not be just enough for me to wipe out the droplets of water from my apron. I want to make it antifungal, antimicrobial, anti-dust, having self-cleaning property in a manner that it will give you assurance that you can go into the most hazardous and virus environment and still smiling in the kit which will be with the doctors as well as the nurses. And this is the lesson we have learned during the COVID-19. And I have great pleasure to say that in our own Amity University, we threw this challenge to our scientists from physics, chemistry, and nanoscience and technology. Can you design something which will be a textile, which will be antimicrobial, antifungal, in fact, anti-dust, and also having self-cleaning property of the kind which Sati Ansuya at Chitrakoot handed over to Goddess Sita to protect her for the next 13, 14 years in the forest. It is that kind of textile which our scientists have designed and developed. We got a patent for it. And we have the capability today in the country. Only thing is our innovations and ideas need to go to the final product so that the industry produces them in bulk, and that becomes really then the solution of the kind we are looking about. And that's where your support and the schemes of the kind which you have presented to us for working together with DRDO and industry, taking ideas to product and product to market, I think holds a great promise. I wish to express my profound gratitude to you and for the support you have lended to our 3-day national conference. Thank you so much, ladies and gentlemen, for giving me this opportunity to share some of my ideas, because I believe that nanoscience is the science of God. And since it is the science of God, it is also science of nature. and therefore it has capability to perform the miracles of the kind which we are waiting, in fact, science and technology to perform. It will make impossible possible. It will give us capability to look after this beautiful world better than what we have done during the last century. And it will give us capability to create a happy and healthy society alongside with the levels of prosperity and excitement of science and technology about which we are so much accustomed to as of today. So that kind of hope is there, in fact, from science and nanoscience and technology. And I have great admiration and support for my own people who are working in my university, including Dr. Thakur, Atul Thakur, Dr. Preeti Thakur, Dr. Krishnaya, and several others who are part and parcel of our larger group. They are working in collaboration with mechanical engineering on one hand, electronics and communication on the other, and also with our allied health sciences and life sciences people to ensure that 360-degree domain of science and technology in nanoscience technology research is pursued. So with the tremendous excitement in our university, Dr. Thakur will share with you some of the patents which we have filed in this area over the last 5 years, and the excitement is truly high. And we want to work with you to take this excitement to the next level, from ideas to innovations, innovation to product, and product to the market. So thank you so much for giving us the window and an opportunity to understand the value and worth of our partnership with you in the years to come. Thank you.
Thank you so much, sir, for sharing your word of vision and your vision of sustainability that is very much required in today's generation. Thank you so much, sir. So,
मुझे ये कहने में बिल्कुल भी संकोच नहीं है that the future will be created on the strength of nano. The power of nano would be most strong in the years to come. And therefore, nanoscientists and nanotechnologists who are working in different colleges and universities should remain excited at the highest level to deliver this promise which we have to God Almighty. Thank you.
Okay.
thank you, sir. So you want to say?
Yes. Thanks a lot, Professor Sharma ji. I have one more point which I want to share. Industry basically is also looking forward for competent manpower. What is happening is defense industry in India is growing at an exponential pace, but at the same time they are not getting the right kind of manpower which basically is required for a defense industry. Defense industry is basically more quality oriented, more stringent production standards. So that kind of a thing, people, many industry leaders, they keep asking us, hey, you suggest somebody, and it's a very nice thing that a MTech course in defense has been initiated at your university, but little more has to be done in this particular area. And I hope that not only defense technology, but all other related fields also, which is related to military defense, that will be taken up in your university as a on a priority basis, because industry needs
very important, of course. What can be done, in my opinion, that all other allied departments, including the applied science department, the engineering departments, they all could motivate their undergraduate as well as postgraduate to take the minor and major projects, as well as several self-study projects, by which they should be able to really align their research abilities towards shaping themselves as tomorrow's manpower for the defense industry. It would be also important for us to open up internships in our defense laboratories as well as in defense industries for the undergraduates of engineering from different disciplines, including mechanical engineering, electronics engineering, computer science, and others, so that we are in a position to sensitize them much earlier in during their studies, so that they align their further actually research focus towards R&D, towards defense. And this can be a win-win situation for DRDO as well as for the universities here.
DRDO on an average is funding 500 PhD scholars also every year. So that is one important area in which, you can have DRDO funded PhD scholars in your university. Right. So in the last, I would like to thank.
If possible, even have scholarships for undergraduate students as well as postgraduate students, because really speaking, we need to catch them young. If I am able to create, for example, 10,000 undergraduate scholarships for those who are aligning their major project toward defense requirement, I think I would do a good job. And that way we are able to sensitize the younger minds and understand the value and worth of aligning their effort towards a cause so important for a nation like ours.
Yeah, this can be taken up as a proposal also. Yes, you have given a very good suggestion that undergraduate programs also can be sponsored by DRDO. Though we are sponsoring our scientists which have joined DRDO, but yes, picking them young, DRDO, did this in early 80s. But after that, that program was abandoned somehow for reasons not known to me. But it can be reinitiated because that time there was a demand of computer scientists in DRDO, and we were not getting it. So in various universities, we started a program in which we totally funded the education of students for computer, basically computer in computer areas, computer engineering and computer applications like that. So, but that program then subsequently, because market was flooded with the computer scientists at a later date, so that program was abandoned. But now, yes, in certain areas, like nanotechnologies.
Today we could think in terms of undergraduate research fellowship for the final year undergraduate student, likewise postgraduate research fellowship for their project. So we don't have to sponsor the whole program, but we can take up the inspired minds and support them through fellowships, and that way they will be inspired to work with our labs as well as in collaboration with the industry, and we create the manpower of the kind that we require.
Similar program, ISRO is doing it for their intake, but that is exclusively for their intake. So thank you very much. Thank you for giving me an opportunity to, discuss about DRDO at this August gathering. I thank Professor Atul Thakur. I thank Dr. Prasanna and all the organizing team, committee, and the participants present over here. Thank you. Thank you very much.
Thank you, sir. Thank you.
Thank you.
Thank you so much, sir. Now we move forward to our next section, which is going to be the online lecture by Professor Sabi Bakar. Professor Sabi has earned PhD degree in electronics from University of Bordeaux in 2012. He has more than 15 years of experience in academia and industry in Tunisian and French companies and universities. He worked on the modeling of high temperature analog and mixed signal circuits. He is currently Associate Professor in Electronics in EC-GELEC and member of IRCM Lab, a joint laboratory with University of Rouen, Normandy, France. His current research works focus on backscatter communication, piezoelectric, energy harvesting, RFID system, and emerging antenna technologies for Internet of Things. Now I request Professor Bakar to deliver his talk. Over to you, sir.
Yeah, thank you very much. I would like first to thank Professor Atul for the invitation, and my colleague Kishore Ajayi for the invitation also. I'm really very happy to participate in this conference for the first time from France. So it's nice, very nice opportunity. Thank you for again for this opportunity. And I also would like to thank the participant who has just finished his presentation. I have found the talk very interesting. Also, I think there are a lot of interesting topics in this conference, and I hope I will participate next year also. So I will share my screen. So how to most of time I use Teams. I am not familiar with Zoom, but I think I will find the Yeah, it's here. Yeah, I'm sorry. Okay. So, okay, I share. Can you see my screen, please?
Yes, sir.
Yeah, thank you. So actually, my presentation will deal with is entitled ambient backscatter communications from the idea to the first prototypes, a brief history, advances, and future challenges. I would like to say also at the beginning of this presentation that I am not material experienced, but I think working with people from many specialties, doing multidisciplinary research, it's very important. I think also it's important for students to be able to understand what is to be able to stand and to have some knowledge about other disciplines, etc. So today I am going to talk about an emergent technique of communications, and this technique would be, or experts suppose that it would be an excellent candidate for the 6th generation of mobile communications, especially for Internet of Things application, IoT application. So I move now to the outlines. So I will give some introduction about this technique. Please, could you precise me the duration of my presentation? It's very important to me.
Yeah, yes, yeah.
How much, please? 15, 10 minutes?
Yeah, definitely, go ahead.
Okay, 10 minutes. 15. 10
minutes.
Hello.
10 minutes. Okay, it's okay.
Hello.
Yeah. Hello.
Atul here. Can you see me?
Yeah, I can.
I'm sorry, previously we could not connect, maybe due to some internet problem, but you take your time. 20-25 minutes you can take.
Okay, it's fine. Okay, thank you, Professor. Thank you. So for the outlines, I will introduce this technique. I will talk about the Internet of Things, emergence of the growth of the number of connected devices, etc.